Now, first let me ask any questions, any issues, any concerns, anything that I can help with.
I don't understand the lab.
Okay, and we have emailed some, right?
Mm-hmm.
Okay, that's where I wanted to start today because I did not have memory enough to record last time, so I wanted to record not everything we did in lab, but just enough so you can see what's going on. Now this is going to kick out from whatever they call screen sharing for a moment, and then, but I'll bring it back because I've got to go and bring in PowerPoint. I can't think what to call it. Blackboard. That's what I was trying to say, Blackboard. I've got all these different things I'm using, and I get their names all crossed up. Okay, it's going to take me a while to get there, but it's coming. Can y'all still hear me? I can't see any of you. Okay, good.
Yes, sir.
Okay. My computer is not responding well. I think it's because I have so many things open at once. Okay. Blackboard is such a pain in the neck to enter. Okay. Now, I'm going to bring y'all back in just a moment here once I get this up. Okay. Okay, do I have you back now? Oh, here's two more, Caitlin and David. David's trying again, but Caitlin hadn't been here yet today. So let me get Caitlin here, and David's coming back again. He said he tried 40 minutes to get into the class last time and could not do it. David, I see your camera's on now, but I don't see a mic yet. I hope you can hear us. Is that David?
Yes, sir.
Okay, right there?
Yes, sir.
All right, good deal. Okay. Glad you made it today. Did you?
Yeah, sorry about that. I couldn't get it to work last time. I have no idea what was going wrong.
I don't either, and it's a mystery to me. But since you weren't here last time, I'm going to move right now to go over the lab that we did last time so that everybody will be on the same page. But the other thing is it's being recorded so that even if people aren't here and weren't here last time, they'll still be able to pick it up. So I'm going to take I'm going to take my screen to Blackboard if I can find it. There it is. Okay. Okay, can you see my working page of Blackboard here?
Yes, sir.
Okay. I'm going to move this block that's in my way down here. You can't see it, but it's in my way. All right, for those who haven't been through it yet, the first day of class, I think I got that recorded on Blackboard okay, and on Screencast-O-Matic and saved to YouTube video. But, okay, wait, here's somebody else coming in. Patrick is here. Let me see who Patrick is. Ah, good deal. Is Patrick Robinson, is that right? Is that right, Patrick Robinson? Hello, Mr. Robinson. Jesus loves you more than you... No, that's a different song. Okay. All right. I hope you're in. So, is Patrick Robinson able to hear yet?
Yes.
You are? Okay. This is your first day here, right?
Well, I was in the first class, but we was on, we did it in the Blackboard. We didn't know that you were doing it on Zoom. But I didn't make it to the second one.
Okay. All right. Well, I don't know if you heard this about the syllabus. Whoa, here's somebody else. Leon's here. Okay, I think it's his first... No, he's been here before. Okay. So Leon's here. But I think he missed the lab last time. So I'm trying to show how to do the lab. And Leon, you here yet? Yeah, I see your. Okay, I'll take that as a yes. Okay, I'm in Blackboard now. I'm not going to go through all this. There's the syllabus. There's my locator card. Research paper instructions. Please read that because that counts as a test score that can't be dropped. Here's the Physical Science 111 YouTube videos. This is what I want to show you. Okay, I'm going to go to that right now. Now, some of this probably isn't all that helpful for Rod yet because you're not in the class and you can't access Blackboard yet. But when you can, you'll be able to reproduce this. So I'm going to the YouTube videos. And for those who are new to the class here that weren't here the first time, the ones you see at the top here are from earlier term. Mostly last spring. Some of them could have even been earlier. The ones at the bottom are the ones from this time. And somehow they got out of order here. And I think I know why. Yeah, I do know why. The first one did record, okay? And this tells you everything. Everything I'm going over now is going to be talked about in that first syllabus with one exception, and I'll explain that in just a minute. Last time, this was the thing. You'll see it ended after only 45 minutes, almost 46 minutes. The computer ran out of memory, which makes no sense at all. This is a almost new HP computer, like a year and a half, and much newer than my old Fujitsu. My old Fujitsu never ran out of memory, and I taught sometimes 4 classes a day, and 3 back to back to back last summer, 3-hour calculus classes, 9 hours of recording. It never ran out of memory. This one ran out of memory after just over, close to 4 hours. So it makes no sense.
Well, there's your problem.
What's that?
HP.
What's that?
There's your problem. You used HP. HP is usually the eye candy brand. It's supposed to look good and be lightly used.
Right. Well, it must be, and it's not candy to my eyes anymore anyway. No, the school provided it. I didn't choose it. Okay. So, to get the rest of chapter 4, and this should be 14. I mistyped that. Sorry about that. On this day of the syllabus, we finished everything and started in chapter 14 and got 14.1 done and into 14.2. This one started at 14.2, but then it ended sometime, probably before 14.4. It died on me, but I don't know exactly when it ended. So I hope that I left. Whoops, sorry about that. Let me get it to scroll up if I can. There it is. Yeah. Let's see if I left. No, I must have deleted it by mistake. So part of what we did last time, you're just going to have to read the book. And hope you get the book. The book is Physical Science by Tillman. What is it? 11th edition? Yeah, 11th edition. You can order it online. You can maybe get it through the bookstore. If you don't want to get the big, thick, heavy book, the bookstore has some books that are less than half this size. They're customized, covering only what we're going to cover in this course. Okay? So you can go with that. Listen to that first video. You'll hear all that. Okay. Now, let me get out of the YouTube videos and go back to the rest. Okay? These are some pictures from Hubble. Now, let me just, for those who aren't used to Blackboard, this icon here means this is just a document. The syllabus is a document. The locator card is a document. Research paper instructions, documents. This is a web link. That's why I could click on that and go straight there. This is a folder. And, of course, Valerie's in the way again, so I've got to move her out of the way. Well, she's not out. Well, she sort of is now. Okay. Over here, you see this is how you open the folder. And these are the 10 really pretty pictures from this Hubble Space Telescope. Nothing you have to do with them. They're just incredibly pretty pictures. A student found them, gave them to me. I said, I'll show these to everybody. That was years ago. Okay, I'm closing that up. Space objects in the perspective, another document. You can look at that, see what it's like. Okay, here's the PowerPoints. That's another folder. Every PowerPoint we're going to do is listed here. And I'll just scroll down. We're in chapter 15 now. Chapter 14, there's the PowerPoints. 15, the PowerPoints we'll be using today. You don't need them unless you just want to print them ahead of time to write on or something like that. Whatever you want to do with them. On the YouTube videos, I teach from the PowerPoints. You see them all there and hear me talking about them at the same time. So that's actually more interesting, or better, I would think. Here's the thing I added since this I added over the weekend, so it wasn't there the first time. This is the evening sky map. I'm going to click on this, okay? Wait. Yeah, evening sky map. And then here, Valerie's in the way again. I just can't keep her out of the way. Okay, now, when you get here, that is the file that it's in. You have to go to the three little dots, click on that, download. Okay? And when you see it finishes downloading over here, then you can click on that. And here is the evening sky map. And you'll notice this is fairly current. I can't find my cursor here. There it is. My cursor just flies all over the place. Okay? Whoops. There's more here than what we did in class. We just basically dealt with this part here. Okay. Can't get it all on, that's most of it. Now let me explain how you use this. You see this little plus sign in the middle of the map? That's where you're standing. Or that's directly above your head where you're standing. That's what they call your zenith. And if you go up into, and what they're imagining here is that the evening sky is like a big bowl, and they call it the celestial sphere. And directly over your head is your zenith. That's that plus. So the star closest to you directly overhead is that little bitty star at the end of Hercules' arm or leg or whatever that is. I don't know. I can't make Hercules out of that. But the closest big star to that, there's actually two here. There's one and there's one. Now I'm going to have to scroll down just a little bit so you can see the, okay, here we go. There aren't any star magnitudes of -1. About the only star that you'll see in that would be Sirius. Sirius is not visible in July. And June. By the way, this is the evening sky map for June 2020. That's now. Okay, today is the 3rd. The moon is the closest it's going to be to Earth in at least a month. Okay, so that's going to be the moon at perigee, closest to Earth. It'll be the biggest moon. It won't be the full moon, but the biggest radius of a moon that you'll see all month. In just a few days, you'll get the full moon. That's on the 5th. Okay, it'll still be a pretty good sized full moon. Okay, that's just letting you know this is pretty current. Okay, now, so when you're looking due north, and I don't know why that's come down in the way. Yuck. I want that to disappear. Let me see if I can make. Okay, wait. Carp's coming in. Capri must have gotten booted out, and she was coming from work. All right, I don't know why it did that. I'd hit the wrong button. See. Okay. No, two more times. Okay. We're back where I should have been. Okay. Now, hold this thought. Hold on to this. Okay? I'm going back to Blackboard for just a moment. If I can find my... Say again?
Professor Fowler, are you about to pull up the questions?
Yes, I am.
I have mine available if you want to
Okay.
read it off.
Well, I want everybody to be able to see them. Okay. Hit the wrong thing, I guess. Where in the world did Blackboard go? Well, Blackboard. Oh, there it is. There it is. Okay. Yeah, there we go. Sorry. All right. Now, here's an important place to recognize on Blackboard. Okay. We're coming back to the evening sky map in a minute. Okay. And why can I not see it? Okay, I'm not close enough to the top. Here we go. You see this icon here? It looks like an envelope. When I get my cursor near it, it says Messages. Go there. Okay, when you go there, you'll find Valerie sent something to me. Okay, and she was late for class. Shame on you. You're the first one here. Okay. Here is your test 1, and here was the lab 1. So I'm going to pull up lab 1. Okay. Well, I thought I was. Again, hit the 3 dots, download, and then once it downloads, click on it again. This is so awkward the way they do it in Blackboard, but this is how they do it. Now, I get this terrible block here in the middle that blocks everything. Now it's not blocking as much. Okay, here is the lab. Now, if you'll notice there, it says list the 2 0 magnitude stars. Those were the biggest stars there, so hang on to that. When facing due north, what position would the clock face would they be? We'll get to that. And what constellations are they found? We'll get to that.
Professor Fowler, my page is blank.
Oh, wait, I'm sorry. I have to do a new share. Sorry about that. There it is. Thank you. Okay. So you can see the first lab. Okay. Find 2 magnitude stars. You write their names there. And you pick which one you want to call 1 and 2. I don't care. But once you pick 1, everything that refers to 1 refers to that one. Until you get to number 2, and then you have another star 1 and star 2. Now you have a star 3 and star 4. But these are different. These are first magnitude stars. These are 0 magnitude stars. And by the way, star magnitudes, they go backwards. 0 or -1 is the biggest. 0 is next biggest. 1 is next biggest. And the bigger the number, the smaller the star. Strange but true. And then again, if you're facing...
Can you repeat that again?
Okay. A -1 magnitude star is the biggest star you'll see. That's Sirius. We don't see it at night now. It's not in view. The 0 magnitude stars are the 2 biggest ones we saw on the star map. We'll go back and look at them in just a minute. There were 4 first magnitude stars. They're slightly smaller than 0 magnitude stars. So as you go up in magnitude, you go down in size. That makes no sense, but that's how they do it. Okay? Sorry about that. Okay? Now, there's another question here. What 3 bright stars form the summer triangle? Once we get out of this, I can't show them both at the same time, but you'll see how to find that. Okay? Now here, Valerie's in the way again. I got to get rid of her. Get out of the way, Valerie. Okay, there you go. All right. I can't get to... Okay. And then, in which constellation is the Big Dipper? The Big Dipper is not a constellation. It's in a different constellation. Okay? And when facing due north, about what clock position would that be? And what constellation is the Little Dipper? And then there's 2 more questions. What star is at the end of the ladle? And what is its magnitude? Okay? Let's go back to... Let me see if it's still here. Well, I had it and now I don't see it again. Let's see if I can find it here. That's not it, but that's...
It's up
Just
top to the
it's
right.
top.
It's up to the top next to messages.
What's that again?
It's up top to your right. We'll say the evening sky map.
Okay, where do you see that?
All the way up top.
At
Go
top.
all the way up top.
Okay. This screen right here?
You on the messenger screen, right? That's what you're looking at? The messenger screen?
Okay.
In other words, he's
Oh,
saying
oh,
click
oh,
on
oh, 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 okay, wait. I think I know where you're talking about. Hold on just a minute. Let me...
Yeah, click on your tab up
Well,
top.
I'm trying to get rid of the thing that's blocking my view. You see, Valerie's in the way again, of course, you know. Yeah, there it is.
sorry.
Okay. Okay, there it is. Okay. It was being blocked by people's names. Okay? Now, remember, I said look down here. As a -1 magnitude star would be a big old circle like that. None of those are viewed. Here's your 0th magnitude stars. Look for that. Those are those two stars, Arcturus and Vega. Okay? Now, remember one of the questions? Say again?
Can you kind of circle around? Because I really can't see.
I don't know what you mean circle around.
Just move your mouse around the area you talking
Okay,
about.
yeah, I was moving it. Okay, you see the mouse now?
Mm-hmm.
In the center. There's Arcturus. The mouse sort of goes away unless I'm right on the zenith. Okay, but it's a little bar there. Do you see it?
Yes, sir.
There's Arcturus and there's Vega. Those are the two 0th magnitude stars. Let's just use Arcturus. You can name them any way you want to. When you're facing due north, there you're facing due north, and remember this square here is directly overhead, directly over your head at night. That would be directly overhead. So you move around the clock face. This would be about 2:30 here. This would be 3 o'clock here. And it looks like Arcturus would be somewhere around, draw imaginary line here down to here, almost 4:30, right? Maybe 4:15. So that would be what on the clock face where Arcturus would be. Now it would be awfully close to directly overhead. So look directly overhead and look behind you about 4:30 on the clock face, and not too far you should see a really bright star. That would be Arcturus. If you go over here to about 9:15 or so, then you'll, and also very close to directly overhead, you see a few little stars in here, but that first big star you see about 9:15, just to your left and a little bit north of that, you will see Vega. So those are the two. So that's what I mean by where are they on the clock face. Imagine this as if it's a clock. North is 12 o'clock, northwest would be 1:30, west would be 3 o'clock, southwest would be 4:30, south would be 6 o'clock, southeast would be 7:30, east would be 9 o'clock, northeast would be 10:30, okay? That's what I mean, just to get an idea of about where to find these stars. That's why I did it. This is nothing magical. This isn't even very scientific to use the clock face, but it's just the best way I could think of to get you so you can identify and locate these stars. Okay? Well, what were the level 1 magnitude stars? These are the ones down here, the smaller circles, not the tiny ones, not these down here, but that next biggest circle after 0. Well, there was one, Spica, Antares, Altair, and Deneb. Okay? There were those 4. And you can number them however you want to. One of them star 1, star 2, star 3, star 4, whatever. Okay? And again, locate those on the clock face. Now, the other thing we didn't do was say, in which constellation are they found? Well, Arcturus was found in Bootes. I don't know if that's how you pronounce it. It's my best guess. That means the herdsman. And supposedly this herdsman is herding this big bear over here, Ursa Major. How they get this, I don't know. But without the lines there, I don't have a clue how they name these things. Okay? Vega over here was just in the corner of Lyra, Lyra. I don't even know what that's supposed to be, but that's for Vega. And then you can pick out the others. Spica, you can see where it was and which constellation it was. Antares in that one. Altair in this one. And Deneb is in this one here. Cygnus, whatever that is. It looks like a cross to me. Okay? The others are slightly smaller than that. I didn't ask for any smaller. I just asked for 0 magnitude and 1st magnitude. 2 and 4 stars. Okay? Also, which constellation are they in? Also, where are they in a clock face? Okay? Does that make sense? Then it asks about the summer triangle. Here are 3 really bright stars in the summer triangle. We've already named them because they are bright stars. That's your summer triangle. So that's just answering that. You don't have to do anything else with that. The next said, find the Big Dipper. There's the Big Dipper. Doesn't that look like a dipper? There's the cup of the dipper. There's the ladle of the dipper. Okay, as we talked about before, and the question is, where is it on the clock face? Well, that looks just about maybe 2 o'clock there, doesn't it? From here to there, maybe right around, no, 1 o'clock. Right around 1 o'clock. Okay? Well, and I pointed this out last time. The last 2 stars in the Big Dipper, and usually you can see the Big Dipper. It's usually one of the easiest things to see. It's not a constellation, though. It's part of the constellation Ursa Major, which means Big Bear. Okay? The last 2 stars on that on the cup point to Polaris. That's the North Star. If you were to look at these stars overnight, go out 2 hours later, 4 hours later, 6 hours later, you see all these stars have moved a little bit, but they've all gone around, but Polaris has stayed right where it is. The Little Dipper here, it rotates around like this. The Big Dipper rotates around like this. Everything rotates around except Polaris. That's what they rotate around. Why? Polaris is directly over our North Pole, so that as we spin, it stays in place. Okay? So, the next question was about the Little Dipper. In what constellation is it found? There it is. It's upside down. Ursa Minor. That means the little bear. How they get a little bear out of that, I don't have a clue, but that's what they call it. Okay? What is the star at the end of its ladle? There it is, Polaris, or the North Star. Where is it on the clock face? If you're standing here, it's basically right at due north. Polaris is at due north. Little Dipper may be a little to the right or left of it. You decide what time you want to name that one. So does that give you an idea how to answer those questions? You look at the evening sky map, which is on under content, and you probably want to print off your the lab sheet, which is under messages. Okay? Now, like I said, Rod, you probably can't even get to either one of those yet. You'll have to wait till they get you in the class. And from what I understand, they couldn't put you in yet because financial aid has the package all tied up now doing Pell Grant. So you'll get there later. Okay. Now, just for those who are interested, in the sky map here, it shows this blue band here. That's the Milky Way. If you live in Birmingham like I do, I've never seen the Milky Way in Birmingham. Out in the farm in Georgia, yes, I see the Milky Way just about any clear night. Okay? That will also help you find some of these stars if you're out in the country somewhere where you don't have all the light pollution. Okay? You'll notice that a lot of these bigger stars are in the Milky Way. Deneb, Vega's right off of the edge. Altair's right in on the edge. Antares right off the edge. They're right there. something we talked about last time, the ecliptic, this is the path of the sun around the Earth, though actually the Earth is spinning, and this is where the sun appears to be. Well, all the other planets always are on the ecliptic. Jupiter is on it, and Saturn is too. Saturn's not very bright. You're going to probably need binoculars to see it. Jupiter probably is going to be as bright or brighter than Vega or Bootes. So if you see another bright object out here, but it's down here around 7:30, 7:45, that's Jupiter. And that's really close to the horizon too. Remember, this is overhead, and these are on the horizon. So Jupiter is just off the horizon, but pretty bright. Okay?
So, Dr.
Yes.
Powell, when it asks for the constellation, you basically trying to find like the time frame for that.
Okay, yeah. Like Arcturus is in Bootes. The stars are given in lowercase, capital first letter and then lowercase. The constellations are all caps. So you see, here's Vega, it's near Lyra. Ursa Minor is the constellation where the Big Dipper is.
Okay.
The Little Dipper is in Ursa Minor. Ursa Major, Big Dipper, Ursa Minor, Little Dipper. So yeah, the constellations are all caps. Like the Cygnus here, that's where Deneb was. Okay? Does that make sense now on how to do the first lab?
Yes, sir.
Okay. Now, the first lab is located in Messages. Print that off, fill in the answer. Your test is under Message. Fill that in, print that off, fill in the answers. Now, here's something that I was just going to say. On June 8th, which is coming up next week, the Moon, Jupiter, and Saturn are within a circle of diameter about 5.1 degrees, which doesn't make a lot of sense to me, but they're pretty close to each other. So if you can find the Moon on the night of the 8th of June, the bright-looking star, it's not a star, that's going to be Jupiter. You might see another dim star close by. The odds are that's going to be Saturn. It's not a star. It's a... Now, if you've got a really good set of binoculars, look at Saturn through the... Yes?
How big is it going to be?
It's going to be... the Jupiter's going to be almost as big or maybe bigger than Vega or Bootes or Arcturus, the two brightest stars in the sky that night. Jupiter's going to be probably really close to their brightness. Saturn's going to be pretty dim. And by the way, Polaris here, remember when we were talking about it? It's not a very bright star. The North Star is not very bright. It's down here probably magnitude 2. Okay?
So you said we'll see it?
Say that again.
We'll be able to see Jupiter?
Yeah, Jupiter is that bright star near the... It's not a star, it's a planet. Near the horizon down there, if you're facing due north, it's to your southeast. It's around... Yeah, and
about
it's...
as bright.
Say that again?
Will it be about as bright as Venus has been?
Not as bright. You won't see Venus. Venus is not in sight right now, but it's not as bright as Venus. Venus is brighter than Sirius most times.
Okay.
Venus is brighter than Sirius.
Okay.
Is that
On the morning sky, if you go out in the morning, you'll see Venus. See, on the 3rd, that was today. If you went out there in the morning sky, you would have seen Venus really early. You won't see it at night. It's on the other side, okay? But Jupiter is close to the same brightness as Vega and Arcturus. It's pretty bright, but not as bright. I don't know if you'll see Saturn. Saturn is down like I'm guessing that's a magnitude 2 star. It's not very bright, but if you have a good set of binoculars, try to find what you think might be Jupiter and look around it and another star, it looks like a star, but it's not, fairly close to it is Saturn. If you have a good enough pair of binoculars, you may actually be able to see the rings. I can't swear to it. I don't have that good a pair of binoculars. But look, it's going to be near the horizon. Where I live, trees cover anything near the horizon. Okay, so probably can't see Jupiter at night from where I live. Okay, but
Okay.
you may be able to if you're out in a parking lot, a football field, park, something without any trees. You may be able to see Jupiter near the horizon, down to the southeast of you. When you're standing here, it would be about 8:45, 7:45.
All right, so real quick, I want to get this established for myself, probably for my classmates as well. So okay, this is the map, and we're looking for the magnitude of each star.
Yeah.
So if I'm facing north, I look north from the Xerox. Is that what you said?
Zenith.
Of the zenith.
Yeah.
And I just go up, which is north, and I
Right.
pick the magnitude stars from that constellation.
Okay, how you get the magnitude, look down here to the right, and you see a -1 magnitude star is that great big black circle. None of them are that big. The 0 magnitude stars, that would be Arcturus and Vega. You see those two? The big dark stars. Those are the two brightest stars you'll see in the sky. They're both near, when you look straight up from where you're standing, straight up, that would be your zenith. To the right, if you're facing north, to the right and behind you a little bit would be Arcturus, and to the left and a little bit ahead of due east, that would be Vega. But they're real close, fairly close to each other, not directly overhead, but pretty close to it. Just a few degrees off directly overhead. I'm guessing, you see, this is going from 90 degrees down to 0 degrees. So with that in mind, 45 would be about here. So this would be maybe 20 degrees, 30 degrees from directly overhead would be Vega, and about the same thing behind you. If you're facing due north, and to the right, you would see Arcturus. These are going to be looking straight up. These are going to be, Jupiter would be looking way to the horizon to your southeast. If you're facing due north, it would be down this way.
Okay, so Vega is a 0, has a star magnitude of 0.
Yeah, because you see here, down here in star magnitudes in the lower right, you see a 0 there. That's the size of Arcturus and Vega. The first magnitude stars are those next biggest stars you see here. We don't have a -1. We just have a first, and that would be Spica, Antares, Altair, and Deneb. Okay? Second magnitude star, I didn't ask for those. There's too many of them. But second magnitude, one of those would be Polaris. It's not one of the brightest stars in the sky. The easiest way to find Polaris, and if you don't know where due north is, find the Big Dipper, look at that last 2 stars in the cup, point to the next brightest star you see, that's Polaris. When you're facing Polaris, you're facing due north. And then you can look at all the others. But Polaris is not going to be nearly as bright as Vega, Arcturus, Spica, Antares, Altair, or Deneb. But it's brighter than most of the rest of them. You can see it.
So,
yes.
My second question is understanding the clock face. Was that like the time of day or?
No. All I'm using the clock face is this. Imagine this is a clock face. Okay? 12 o'clock would be due north. 3 o'clock would be due west. 6 o'clock would be due south. 9 o'clock would be due east. Just imagine that's a clock, right? So yes. Northwest would be about 1:30. Southwest would be about 4:30. Southeast would be about 7:30. And northeast would be about 10:30. So then estimate where those stars are. If you're facing due north, this one would be down here about, I was guessing, 4:15. You may make a different guess, okay? That's up to you. Looking over here at Vega, I was guessing about 9:15. It's a little bit north of east. So I was just guessing 9:15. Those aren't exact. That's just to give you an idea, if you're facing due north, where you can see these other stars. Otherwise, you go out there and look up and say, what's that? Where are these? If you can face due
Dr.
north.
Biden, can you point to Antegras again, or however you pronounced it?
Point to what?
I think you said Antegras or something.
There's Antares. Antares is down here. You see it?
Okay.
Is that the one you meant?
Yes, sir.
Okay. Altair was over here. Okay.
That person is funny for that.
What's that again?
Oh, someone messaged something in the group chat.
Oh, okay. I'm not keeping up with chat. I've got too many things open now. Is there something I need to answer?
Oh, no. It was,
Okay.
I think this is going to be my last question because I think I have it down pat. My last question is, so when I'm looking at the assignment, it says like star 1, star 2. Am I going to put different stars?
Yeah, you pick 4 magnitude 1 stars. The ones I picked were Spica, Antares, Altair, and Deneb. Now that I look at it, I wonder if Regulus is 1 too. But I only put 4. You choose 4. I think Regulus is a little smaller, so that's why I went to Spica. But I'm not too sure. You pick any 4, and then you give the information on those 4. There are only 2 magnitude 0 stars, that's for sure. You pick which one you want to name number 1 and 2, and then give the information according to that.
Okay.
Does that make sense?
Yes, sir.
Okay. No. So Rod, when you finally get in the class, you'll be able to do all this. Now you'll know where to look and do it. Cormisha, does this answer the questions you were having?
I think so.
Okay. And then your test is out there, the same place the lab was. That's under messages. So go get your test then, and your lab. Use this evening sky map to answer your lab. The evening sky map is under content. It's the last thing under content. All right. Ready to get back to class? Can I turn this off now? Turn off the evening sky map. And I think I'll turn off messages too.
Let's learn some more about space, man.
Okay, well, we finished with the universe. Now we're getting ready to go to the solar system. Are you okay with that?
It's not as much, but it'll do.
Okay, so let's go to the solar system. All right. We'll go from current slide. This is chapter 15. All right. Now, what you see here in this picture, they don't tell you for sure. Can everybody see this picture? Chapter 15, Solar System, PowerPoint lectures, right?
Yes.
By the way, this is Physical Science 8th edition. This is 3 editions ago, so this isn't quite up to date, but these are the last PowerPoints they sent me, okay? Now, I think, I'm not absolutely certain, I think that's probably Neptune. I don't know that for sure, but Neptune is a bluish-looking star. It's way out there. My guess this was taken by one of the satellites that they sent way, way out there to space. Okay? You don't need to know that, but this is just beginning the solar system. Here is the core concept. If you have the text, this is on page 378. If you have the little text, probably the number will say 15-1, meaning chapter 15, page 1. Okay? And here's what it says. The solar system is composed of, number 1, the sun. That's where they get the name solar. S-O-L, sol means sun. The solar system and orbiting planets, we now have 8 of them. Okay? We used to say we had 9. They've kicked Pluto out of being a planet and named it a dwarf planet now. Okay? So they say orbiting planets, now the dwarf planets. The book mentions 5 of those, and we'll talk about those 5, but there's probably others that qualify, and then small solar system bodies. And they do list a few of these here, and these few that you can see, if I could get my thing, here is the asteroid belt. Those are some smaller bodies. Of course, a lot of the planets have moons. Those are smaller bodies. Flying around out here somewhere are comets. Those are smaller bodies. So there's a bunch of these smaller solar system bodies, many, many of them. Now, let's look at this picture a minute. Do not ever, in the least bit of your imagination, think that the planets and the solar system ever look like this. Number one, if you were to draw the sun, it is so much bigger than anything else out here. In fact, looking at this, it looks like the sun is not too much bigger than Jupiter, say. No way. No way. If you were to draw the sun its regular size, Jupiter would be a speck. Earth would be less than a pixel, okay? So the sizes here are not relative. Now, the sizes of the planets are not far from what they should be relative to each other. They're nowhere close to what they should be relative to the sun. Otherwise, your picture would be completely out. Now, the distances. Mercury is the closest to the sun for sure. Venus is next, Earth is next, and Mars is next. These aren't quite precise, but they're not far off. The asteroid belt is probably pictured a little too close here, and everything else is way too close. These things, as we're going to learn as we talk about this, they get farther and farther and farther away, okay? When you finally get to Neptune up here, if you had everything else according to the scale here, Neptune would be in the next room. I mean, it would be way, way away, okay? So the scale is wrong. The relative order is okay. The relative sizes just among the planets, and really even the moons, not too far from being okay. But most of the rest of it, the scale is completely off, okay? So that's what we're looking at for this term. For this chapter, okay? So beginning in 15.1, planets, moons, and other bodies. Okay, now all this is governed by the International Astronomical Union, the IAU. That is indeed international. It's not U.S., it's not any one nation, International Astronomical Union. They are the governing authority over what names of these things are, what classifications, all that kind of stuff is determined by the international, the IAU. The IAU has come up with definitions for what is it that a planet is, what is a dwarf planet, and what these smaller solar system bodies are. Okay, some of them I find sort of confusing. They call some things asteroids that I would have thought would have been comets, but no, they call them asteroids. Okay, fine. Back in 2003, and I think most of you were alive then, but maybe not all of you, Pluto was redefined. Before that, it was counted our 9th planet. They redefined it as a dwarf planet, according to the... I'm sorry? Was there a question? So Pluto is not considered a planet anymore. It's a dwarf planet. Okay? Now, you don't have to know, and we're not even going to go into all the nitty-gritty of what makes a planet, a dwarf planet, not a planet, and the other small system bodies, what they are. I'll give you just a few general ideas. Okay? To be a planet, you need to be a pretty big object. Pluto is not very big. Okay? Now, of the planets, let's go back to that earlier slide. The 4 innermost planets, notice they're much smaller than the other planets. These are huge things, okay? They actually call them gas giants, and there's a reason for that. We'll talk about it later. These 4 in here, though, are called terrestrial planets. What do we mean by that? They're made out of rock. They're hard. They're not gases. The 4 out here, the surface is not rock, It's nothing solid. You couldn't stand on the surface of any one of these planets. You would fall through. You wouldn't be able to tell the surface from the atmosphere. It's just a continuum there. It just sort of define them that way, okay? So these are hard, rocky planets. These are gassy planets, okay? So there's a difference. What was Pluto? Pluto was somewhere out here. It was smaller than the smallest terrestrial planet. It was smaller than Mercury. So its size didn't fit. To be out here, you would have thought it would be a gas giant. It wasn't. It was a small rocky planet. So that was one thing. Too small. In fact, I'm almost certain that the Earth's moon is larger than Jupiter. In fact, the Earth's moon's not too far from being the size of Mercury. In fact, Saturn has a moon that's actually bigger than Mercury. I think Jupiter may have 2 or 3 moons that are bigger than from Mercury. So, yeah, size is everything, but Pluto was way too small to be counted a planet. Now, that's one thing, okay? Another thing. Now, this is something this picture almost does well, but remember when we were looking at the ecliptic, that dotted line on the night sky map? Remember when I pointed that out, and Jupiter and Saturn were near that dotted line? The ecliptic defines this plane where the sun is in the center and all the planets are going around it. The planets aren't here, 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 and there. They're not like that. They're all in the same plane. And that's why I said Jupiter and Saturn were right there near that dotted line. All the planets are there. But not Pluto. Pluto was way off. It was like 17 degrees off that plane. So that was another thing that knocked it out from being a planet. There may be some others. We're going to leave that alone. Oh, yeah. Here's one more. Most of the planets form orbits. Now, they may look like here they're circles. They're not quite circles. They're what we call ellipses. Ellipses are a little more elongated, okay? Not perfect circles, but a little bit elongated, okay? But not far from being a circle. And we'll talk about that later, too. Pluto? Oh, it was really elongated. Sometimes Pluto was closer to the sun than Neptune was. Here's Neptune, the last one out here. Most of the time, on average, Pluto was somewhere way out here, but sometimes it was actually closer to the sun than Neptune. None of the other planets cross each other's territory like that. So that's another reason Pluto is no longer considered a planet. But now it's called a dwarf planet. Too small to be a planet, and some other characteristics that are not. Okay? Well, the IAU was what determined that. Now, all right. What then is our solar system made up of? Well, Sol means sun. At the center of the solar system is our sun. Now, I want to point something out to you that later seems like it's contradicted, but they just didn't word it right. And I'm going to read it directly out of the book. If you got your books open on page 379, on the right-hand column, the last paragraph on the right-hand column, the sun has 700 times the mass of all the planets, all the moons, all the minor members of the solar system put together. So that's why I said that figure that we saw at the very beginning, nowhere close. If you were to add everything up here, all the planets, all the moons, all the asteroids, all the comets, all the things you don't see on here, add them all up, the sun is 700 times bigger than all those put together. Okay, that's why I said the sun is nowhere close to being in scale with the planets. Okay, now later you'll see a statement that makes it sound like that's contradictory. They just misstated it. Okay, and I'll point that out when you get there. Okay, now we have 8 planets. We used to say we had 9, don't have 9 anymore, we have 8. Pluto was reclassified to make it a dwarf planet. Okay. Now, this is an estimate. Something on the order of 100 moons going around the planets, various planets. I say it that way, but that's not quite true. Mercury, 0 moons. Venus, 0 moons. Earth, 1 moon. Mars, 2 really small moons, but 2 moons. So where do they get 100 moons? All those gas giants out there, they have tons of them. I think Jupiter alone has anywhere from 50 to 70 moons. Okay? Saturn has a lot of moons, not as many as Jupiter. And Uranus and Neptune have a lot of moons. They're so far out there, we don't know exactly how many they've got because moons are pretty small and it's hard to tell. But they have, I'd say, in the teens. You can look that up and find it. Okay? Now, so 100, somewhere in the neighborhood of 100 moons or more. Thousands of asteroids, millions of these icy bodies. Now, the icy bodies are sometimes comets, sometimes not. So there's a lot of stuff out there, a whole lot of stuff. Now, how do we measure distances in our solar system? Now, we know in the universe we measure in light years because things are so way far apart. In our solar system, we use a different unit, and it's called an astronomical unit. That's not Auburn University, that's an astronomical unit. And what is that? That is the average distance between the Earth and the Sun. So that's about 93 million miles on average, which is about the same as 15 million kilometers. Okay, that's not right. 150 million kilometers. Okay, 93 million miles are about 150 million kilometers. That's a long distance, but guess what? That's nowhere. That's a small measure of our solar system. That's something we use to measure the planets. Okay, things outside the planets we go back to light years. Okay, now the planets are classified several ways. By size, and I've already talked about that, Sun. The 4 inner planets are smaller, but they're denser because they're made out of rock. Okay, so they're classified by size, also by density, and then also by atmosphere. Some planets have no atmosphere. Think Mercury. And Mars is very thin atmosphere. Earth has a great atmosphere. Venus has an even thicker atmosphere than the Earth does, and then the others are something else. So part of that planet classification is breaking it into 2 big classes. I mentioned this before. The terrestrial planets, you could also call them rocky planets, and then the giant planets, which is mostly gas planets. They call them the gas giants. The 4 inner planets are your terrestrial or rocky planets: Mercury, Venus, Earth, and Mars. These all are the densest planets, the greatest density. They're mostly rocky materials like stone, rock, iron. Actually, in their core of all of them is mostly metallic nickel and iron. Iron predominates, but some nickel as well. In the gas giants, those are the 4 outer planets: Jupiter, Saturn, Uranus, and Neptune. These are mostly hydrogen, helium, and methane. So they're gases. They're not solids. Now, I'm not saying they don't have some solid part to them, because somewhere down in the core of those things, it's so dense that they may actually be solids. But most of them are made out of those 4 gas giants are hydrogen, helium, and methane, which I find methane really interesting because I think of methane as being it's a carbon compound, And why in the world is carbon there if there's no life there? Well, carbon exists. We'll find that out later. Pluto, no longer considered to be a planet, but a dwarf planet. So at this point, because they don't mention that in the PowerPoint, but I do want to point out to you in the book, what are some of these other dwarf planets? Like I said, we know of 5 they've named so far. And this again is on page 379, the right-hand column. It's actually above what I was talking about before. There are 8 planets, at least 5 dwarf planets. Pluto being the main one, the one we know best. Then there's one called Eris, E-R-I-S, one named Ceres, that's C-E-R-E-S, and the next 2 sound like they're Hawaiian names. I don't know if they are. The first one is Maki Maki, okay, sounds like some sort of drink or something, and the other one is Haumea, okay. I don't even know if I'm pronouncing them right, but those are your 5 dwarf planets that we have named and classified now. Pluto, way out there. Eris, I've tried to remember, it seems like it's somewhere fairly close to Saturn. I'm not sure, I may be wrong on there. Ceres and Maki Maki, and maybe Haumea too, are actually really big asteroids. Okay? I'm not sure on that either. They don't talk about much of them in the book, but you can study that, read about it. You can even make that your paper topic if you wanted to. Okay. Now, and of course, based on an astronomical unit, Earth is 1 astronomical unit from the sun because that's our average distance from the sun. The inner planets are closer to the sun than that. The outer planets are way further out than that. Okay, so let's move on to the next slide. Okay, here's that same picture we had before, except this one includes Pluto. Pluto is no longer a planet. Never will you ever in 1,000,002 years find the planets lined up like that. This is just some artist's conception. Again, just picturing the sun in here, nowhere close to the right size. The planets are relatively well-sized, okay, compared to each other. A thing to note here, and this isn't quite true but close, the Earth's moon here is not quite sized properly but close. It's almost as big as Mercury. Some of the moons of Jupiter, like this one, that one, and possibly these 2, are basically almost as big or bigger than Mercury. Saturn has a really large moon. I think it's either this one or that one, is called Titan. You may have heard of that. I believe it's larger than Mercury. Okay? And then they just have representative moons around Uranus and Neptune. It looks like a lot of them. I think if you were to count all these, you'd find out it probably adds up to more than 100. But you can't even see them all, so don't even bother. Now, this is a little disturbing. Pluto, way out here, is much smaller than Mercury. It doesn't really look like it in this picture, but it is much smaller than Mercury, much smaller than our moon, than several of the moons of Jupiter and Saturn, and probably some of these other planets as well. This should not be listed as a planet. And the other thing is, the distances in here are not too badly off. They are a little bit. Out here, they're way too close because they had to fit them all in one picture, so they really crammed them together. So that's just the order of the planets. Mercury is closest, Venus is next, Earth is the 3rd rock from the sun, if you remember that television show. Mars is out here, then the asteroid belt, then you hit the gas giants. The biggest, by far the biggest, is Jupiter, then Saturn, and then Uranus and Neptune are almost the same size. We'll study each one of them separately. So any questions on what we've done so far? Now, there is one of these examples that you really don't need to do, but it says, how long would it...
I'm sorry, you're going out.
Okay, I have to move my book in front of me. Okay, this example 15.1. How long would it take to travel the average distance between Sun and Earth in a typical jet airplane speed of I guess that's 1,000 kilometers per hour using the equations from section 2.2. 2.2 was way back in the first part of the book, so you don't need to know this. But the answer may be interesting to you. The answer, it says, is about 2 months of travel, about 62 days to go if you could fly a jet plane from the Earth to the Sun, okay? To travel the average distance between the Sun and Earth, about 2 months. So our fastest jet plane, not going to work. Well, number one, it won't work outside of our atmosphere, period. But if you could, and you flew to the Sun, well, there was a Greek story about somebody who tried to fly toward the Sun and wound up getting killed, okay? So you don't want to go there either. But if you could, it would take about 2 months. So anyway, there is a second one there. Interplanetary space probes travel about 7.3 kilometers per second, not per hour, but per second. How far could it travel in a year? About 2.3 times 10 to the 8th kilometers. That's 230 million kilometers. Okay? That sounds like a lot. It really is just barely not quite twice the distance from here to the Sun. So space travel, even in our little bitty old solar system we have here, takes a long, long time. For instance, when they send a probe to Mars, okay, here Earth is and here Mars is, it takes literally months for it to get there, because never is Mars sitting that close to the Earth. What you have to do is send, when Earth is over here and Mars is over here, you send it up and try to intercept Mars coming around. You never try to do it if Earth is here and Mars is over there. You're never going to make it. Okay, it would run out of fuel before it got there. So yeah, it takes a long, long time for you to get even from here to Mars or here to Mercury. Here to the moon takes a while. That would be hours, but you know, whatever. All right, let's move on to the individual planets. That's what we're going to look at next. And before we do, some of the information here is found in the table that to me is the most informative table in the whole book, okay? Not just this chapter, in the whole book. Okay, here's what the table looks like. I know I'm blocking the microphone. Okay, I don't know if I've even got it. Okay. It has tons of information in that table. Now I'm going to point out some of it to you right now, but then we'll hit other parts when we see the individual planets. Okay? Now, the first is the average distance to the Sun. I don't think in terms of millions of kilometers, so I'm not really worried about that. But in astronomical units, which would be the average distance from the Earth to the Sun, Mercury is about 0.38 from the Sun. Now what does that mean? Less than half an astronomical unit, a little over a third. It's more like 3/8 of the distance from the Sun here, Earth here. Mercury would be about less than half, more than a third of the distance, okay? Really, really close to the Sun. Now, I said that most of the planets have fairly close to circular orbits. None of them are exactly. They're all ellipses. Mercury has the most elliptical orbit, now that you don't count Pluto. When Pluto was there, Mercury looked like it was circled, okay, because Pluto is way, way elliptical, but it has a highly elliptical orbit. Its average distance from the sun, like I said, is about 0.4. The table says 0.38. This rounded to 0.4. Now, here's kind of an interesting point. The average period, orbital period, for the Mercury to go around the sun one time is about 3 months. Of course, it takes us 1 year to go around the sun, 12 months. So we go around the sun Mercury goes around the sun 4 times while we go around once. So you see, there's no way all those planets are ever going to line up the way those pictures did. They're going at different speeds. So the orbital period of Mercury is about 3 months. Now the rotation of Mercury, though, rotation of the Earth, we rotate once every 24 hours. That's what makes our day, right? Well, guess what? The rotational period of Mercury is 59 days. Not 59 hours, 59 days. So that means it turns 1.5 times for every time it goes around the sun. So its day is 2 months, its year is 3 months, okay, in our months. It's a weird, weird situation. The rotation of Mercury is really, really slow. Now, I have a theory on why that's the case, but I've never seen anyone else say this. But Mercury has been pummeled by so much mess. Because you see, the sun draws all sorts of things to it, and Mercury's in the way. It's real close to the sun, and it gets hit by stuff all the time. And my guess, that's why it slowed down its rotational spin. I may be wrong on that, but that's my guess. Now, can you ever see Mercury? I'm not sure I've ever seen it. And why? Well, picture here. Here's the sun. Big, big, huge, bright sun. Mercury, this tiny little rock that's going around it. Really close to it, though. Okay? Venus is out here, about twice as far away. Earth is out there almost 3 times as far away. Okay? So when is Earth going to see Mercury? It's so close to the sun, you won't see it because the sun is so bright. The only time you'll see it, if the sun happens to set under the horizon of the Earth while Mercury is still on the outside, you may see it for just a few seconds. But it's going to be so close to the horizon because the sun just dipped below the horizon, and it's so tiny, the odds are you'll never see it. Okay? Or just before the sun rises, it may be Mercury is on the upper part of its thing, and you may see it again for just a few seconds, but in no time, the sun's going to come up and bleach it out. You'll hardly ever see Mercury. Okay? It's visible shortly after sunset, shortly before sunrise, and when I say shortly, a number of seconds. Maybe as long as a minute or 2, but not much more than that. Now, remember I said they classify planets according to their atmosphere? Mercury has 0 atmosphere, no atmosphere at all. Okay? And since it has no atmosphere, it has nothing to stop anything that wants to hit it from hitting it. Now, there's lots of stuff flying around the Earth too, okay? Out there in the atmosphere, or actually we're flying into it. But you see, our atmosphere is so thick that most of it burns up before it reaches the ground. That's what we call shooting stars or falling stars. The real name for them are meteors or meteorites, okay? It's the stuff that's out there that hits our atmosphere, gets sucked into the Earth, and burns up on the way down. Now, every now and then, a rock will make it all the way to the Earth, and we call that a meteorite if it makes its way to the surface. But if it burns up out there, it's just called a meteor, or a falling star or shooting star. Now, Mercury, that doesn't happen. That same stuff that comes and hits our atmosphere and burns up, on Mercury, it crashes into the planet because there is no atmosphere to slow it down or burn it up. So Mercury is a highly cratered planet. We'll see other things that are too, and they have no atmosphere or very little atmosphere. And Mercury, now that Pluto's not even considered a planet, Mercury by far is the smallest planet. Okay? Now, here's what they mean by Mercury just being visible. See, once that sun comes up and peaks above the horizon, or before it sets and goes below the horizon, you'll never see Mercury. Even though it's out there, you'll never see it. Once the sun finally drops below the horizon, or before it comes above the horizon, you may see Mercury for just a few seconds, no more than a few minutes. Okay? Now, Mercury has phases just like the moon does. When Mercury is on the far side of the sun, that's when it's a full Mercury. But guess what? It's so far away and almost lined up with the sun, you'll never see it. Okay? You may see it a little better when it's here and it's a smaller portion being lit, but more. Here's Mercury at half a Mercury, and that's here. Here's when Mercury is closest to us. When it's closest to us, none of it is illuminated by the sun. Just that little sliver would be all. So it's going to be hard to see there because so little of it is visible. Okay? So you'll hardly ever see Mercury. I don't know that I ever have. Okay? Now this is actually a picture of Mercury. Now how they took this was several passes of satellites that they took pictures of what they saw, and then scientists sort of patched them together. And that's why it looks like there's lines here. There really probably aren't those lines there. That's just where the different satellite pictures had slightly different colors or other things to them. But look at that. Look at that surface. If I can get my cursor to show up. There it is. There's pits and pits and pits, craters and craters and craters, because everything smacks into Mercury. There's no atmosphere to stop it. They just come and collide. And because it's been hit so much, so often, so many times, my guess, that's why it slowed down its rotational period. That's just my guess, though. So there's Mercury. Small planets, the smallest planet, no atmospheres, no moon, nothing, okay, except a lot of craters. Now you might say, since it's closest to the sun, is it the hottest planet? Well, that depends on what you mean. The side of Mercury that's facing the sun, and just looking at this Mercury, the sun is right up here somewhere, maybe a long way away, but right there. Because this part of Mercury is not being lit by the sun, the part that is here, so this part is closest to the sun. Right there, probably, yes, it's probably as hot as anything planet in the solar system, right there on the surface, closest to the sun. But you see back here, on the back side of Mercury, oops, Leon, I think I already had him here, didn't I? Yeah, I already had Leon here. He must be coming back. Okay, on the back side of Mercury, down here, if I could get my cursor to show back, down here where it's nighttime on Mercury, where the sun's not shining, it's frigidly cold. Now what makes a difference? There's no atmosphere here to hold the heat in. So as soon as it spins away from the sun and it becomes night, the temperature drops like a rock. I mean, it goes from being burning hot when it's facing the sun to frigidly cold when the sun's not shining on it anymore. It drops and drops and drops. So no, it's not the hottest planet on average. Yes, on that position right there, it probably is the hottest. But on average, it's not, because it's frigidly cold on the other side when it's in darkness. And remember, it doesn't spin that rapidly, so it's going to be hot for a long period and then cold for a long period, any particular point on the sun, on the Mercury, on the surface. Okay, I can't get my slide to advance. I have to click here. All right, let's move from Mercury to Venus. Now, what I want you to look at first, well, we'll look at these things. These are on your table. Always go back to the table. There's a lot more information in the table than you'll find on the slides. The orbital distance of Venus is about 7/10 of an astronomical unit. In your table, it says 0.72, okay? So it's almost 3/4 of the distance from the sun to the earth. Venus is much closer to the earth than it is to the sun. Mercury, much closer to the sun than it is to the earth. Or even than it is to Venus. Closer to the sun than it is to Venus. Now, Venus is a planet, but it's often called either the morning star or the evening star. And like one of you were asking when I was showing the star map, it is right now visible in the early morning hours. Just before sunrise. If you go out there before the sun comes up, and at this time of year, that's pretty early, let's say 4 o'clock or earlier than that, and you see a very bright object in the sky that's not the sun and not the moon, that's Venus, because it is brighter than any star out there. Now, it's called the star because it looks like a star. However, if you looked at it through a good set of binoculars or a telescope, you see it's actually a planet. It's actually a planet. You don't see anything coming out of Venus. You only see light reflected off the sun off Venus, from the sun reflecting off Venus, and that's why you are able to see it. It's far brighter than Sirius, far brighter than Jupiter, far brighter than any of the things we saw on the evening star map. It's next to the moon is the brightest thing out there, but it's not always out there. Now, it does have phases, just like the moon and just like we saw Mercury did. Sometimes you'll see a full Venus, and that'll be really bright. Sometimes you'll see half of Venus. That'll be sort of bright. When Venus is closest to us, all we see is the dark side, and you won't see much of it at all. Okay. Now, this is, to me, one of the two strangest things about Venus. Every other planet, including Venus, everything in the solar system goes in a certain direction around the sun. All the planets go in the same direction around the sun. And all the planets spin in the same direction that they're going around the sun, except Venus. It spins in the opposite way from what it's going around the sun. So if you were on Venus, you don't want to be on Venus, but if you were on Venus and you looked out in the early morning, the sun would be rising to the west and setting in the east, backwards from the earth, because it's spinning backwards. Now here would be the other strange thing. It takes longer for Venus to spin one time on its axis than it takes for it to go all the way around the sun. Its day is longer than its year, you might say. Because a year is how long it takes to go around the sun. A day is how long it takes to spin once. Venus day is longer than a Venus year. Now, and it's also going backwards. So those are weird things. Here is one speculation. I think the book mentions it, but if not, it's somewhere I've heard it before, of why that may happen. Remember when we were talking about how a star is born, okay? Remember, that's not a Barbra Streisand movie, that's something else. The stars started as a mass of gases, but they weren't stars then. When they came together hot enough to start fusion, they became what they call a protostar. The protostar was exploding nuclear fusion, pulling in gravitational. It was a mess, okay? And after a while, it finally reaches that dynamical equilibrium, which sort of fixes its diameter and stuff, and then things settle down. We'll talk about that more later in this chapter, okay, especially with regard to our sun. Okay. during that time is when the planets form, when stuff is being spewed out of the sun, but then things are being pulled back in. Things are hot, they're radioactive, they're a mess. Slowly as they cooled, they solidified. Those that did solidified, like the rocky planets. Okay? Now, sometime in that time frame when all that mess was being thrown around in our solar system, more than likely Venus got hit by a really, really big object, and may have got hit so hard that it changed from spinning this way to spinning very slowly in the opposite direction. That's the theory of why Venus did that. Now, Venus is our closest planetary neighbor. Our closest neighbor is the moon, of course, but it's a planet, it's a satellite of our own. The other planets are going around the sun just like we are, and Venus is the closest planet to us. It's closer than Mars by quite a bit. So therefore, it has been visited by numerous probes. In fact, just about every probe we send anywhere, we run it by Venus first, and what it does, it loops around Venus and sort of slingshots away. It saves on fuel that way. It's bizarre but true. Okay? Now, it has an incredibly dense atmosphere. That atmosphere is mostly carbon dioxide, which I found to be fascinating in itself, because I always thought carbon dioxide came because people were breathing it out. Okay? No, that's not where carbon dioxide comes from. Carbon combining with oxygen in any shape or form forms carbon dioxide. Most of Venus's atmosphere is carbon dioxide. It's an incredibly high temperatures and a very dense atmosphere, so it's incredibly high pressures, way more than the Earth's atmospheric pressure. So you don't want to be on Venus. Even if Venus is for lovers, you don't want to be there. Okay? Even if women are from Venus and men are from Mars, you don't want to be there. Okay? Because you would die. Okay? Number one, it's so hot you'd burn up in a moment. Number two, the pressure is so great you'd be crushed while you're burning up. And the atmosphere is mostly carbon dioxide, you wouldn't be able to breathe. There's hardly any oxygen there except in the form of carbon dioxide. So yes, you don't want to go there. Now, remember, Mercury, no atmosphere. Venus, an incredibly dense atmosphere at incredibly high temperatures and pressures. Now, why the high temperatures? Now, time out a moment here. In the news, you'll hear a lot of people talking about, less now than it used to be, but it still should be talked about a lot, global warming, right? You've heard of that, right? Now, what contributes to global warming? There are certain gases they call greenhouse gases that contribute to global warming. Does anyone remember what some of those are? One of the major ones is carbon dioxide. So number one, Venus has more atmosphere than the Earth does, a really dense atmosphere. Number two, most of that atmosphere is carbon dioxide, a greenhouse gas. And what greenhouse gases do, they trap heat from the sun. So here Venus is second closest rock to the sun, planet to the sun. So it's pretty close to the sun, a really, really dense atmosphere. So therefore, it traps the heat. So on average, Venus is far hotter than Mercury. Mercury has no atmosphere, nothing to trap the heat. It's really hot when it's facing the sun, incredibly cold when it's away from the sun. Venus, hot whether it's facing or away from the sun. It's really dense atmosphere, traps the heat, and it's really high temperature. Sure, I'm sure there's a swing in temperature between facing the sun and not facing the sun, but still, it's hot. It's incredibly, incredibly hot. Now, what's the surface? The pictures they've taken as cameras have gone in, mostly flat, but varied. And when I say varied, I wish we got to go to the planetarium. We don't get to go because everything's closed down. But it has some incredibly tall volcanoes on it. So not only is it hot, it has active volcanoes which are spewing out lava, more carbon dioxide, more sulfur dioxide, more really bad stuff you don't want to breathe. Really acid environment. You don't want to go there. And that's why I'm pretty sure if we've ever had a satellite to land on Venus, it didn't last very long. Okay, someone's trying to come in. I can't see who it is. I still couldn't see who it was. Is that someone new coming in, or is someone that's already been here and gone out and come back? Does anyone know? Okay. If you do come in late, please say something so I can mark you on the roll. But right now, this is just so far, I don't...
Something happened with my Wi-Fi.
Say again?
Something happened with my Wi-Fi.
Okay, so you were here before. Okay. So far, I haven't seen Don Baldwin. Has any of you? I haven't seen Bridget Cockrell. I haven't seen Juan Jackson. Now, if you've seen any of these names, please let me know. Today, I mean. Scott Lucas. Now, I heard from him. He was, I thought it was going to be back today, but he was on a trip with a nephew, so I thought he would be back today. Haley Mason, we haven't seen from the beginning. And Anthony Trey Main Wesson, we haven't seen from the beginning. So if any of you are out there, please let me know because I don't have you marked here today. All right. So that's most of what we know about Venus. The most unusual things about Venus, its day, one spin of around the axis is longer than one trip around the sun. Pretty amazing. Okay? Number two, it's spinning backwards. So not only is it spinning slowly, it's spinning slowly backwards. Okay? Just to give you an idea, Venus's orbital period in Earth years, that's how long it takes to go around the sun, is about 6/10 of an Earth year. Okay? Which means a little over half a year. Something maybe around 7 months. That's how long it takes Venus to go around the sun once. So its year is about 7 or 8 months, something like that. What is its rotation period? Well, it's actually a negative number, and it's 243 days. So that's basically more than 2/3 of a year it takes to spin once, where it only took 6/10 of a year, slightly over half a year, to go around the sun. So that's why its day is longer than its year. All right, the rest of it you can probably get. Please look at the table, okay? Pretty interesting information there. Now here, yuck, I have to click on the screen before I can pass it. Here are some of the probes. Like it said, visited by numerous probes. Here's some of them. Now, interesting to me, to note who own these probes. And if you'll see, USSR, does anyone remember who that is? It was called the United Soviet Socialist Republics. We called it Russia, but Russia was just the biggest of the Union of Soviet Socialist Republics. Russia was the biggest one. It was the USSR, the Soviets, Russia was what we usually called it, but Russia was just the biggest of those. Back then, Ukraine, Belarus, Chechnya, there were just I think some of the stans, Kazakhstan, and several of those were in Siberia. They were all constituents of the Union of Soviet Socialist Republic. Russia was just the largest of those, so we called it Russia, and the capital was Moscow. Okay. Now, if you'll notice, USSR was leading the space race going to Venus. They really beat our socks off there. But what we did, since they were going to Venus, we decided to go to Mars and the Moon and places like that. We did have them that went by, and when you see flybys, that means they were going by Venus on the way to somewhere else. Okay? They had one, I guess by design, crashed on Venus, impacted Venus. All these indicate that. Now, here was my guess from before. If we ever were to have a probe that tried to land on Venus, it would probably get so hot, parts of it would melt before it got there. It may actually burn up before it got there, like a shooting star here. Almost certainly it would cease to function before it reached the surface. And if it ever did reach the surface, it would probably decay away really quickly because it's so acidic. So we don't have very many successful Venus landings that have sent back any information except what they get on their way in. Okay. Now, there are some that come from the U.S., and they're mentioned here. Notice, whoops, here's somebody. Oh, Thomas is coming back in, I guess. Notice that most of the interplanetary space travel was between 1961 and 1989. You know, that was what, 28 years, and it has been more than 30 years since anything else happened, okay? Yuck! We've really cut back on our exploration of even our solar system. Back then, we seemed to have more money and more interest and more desire. Nowadays, I don't know. Mystery to me. Okay. Yuck. I have to touch the screen. Okay. Here is that picture of that volcano I was talking about. My understanding is this is actually a larger volcano than any we have on the surface of the Earth. Whereas they said the surface was mostly flat but varied, that's some sort of variation there. Now, what is this mess here? That could be a river of lava, molten rock. It is so stinking hot on that planet. And if you have volcanic activity, it's not going to melt in a hurry. So you may have molten material floating around out there. That's not water. Water would have evaporated a long time ago, okay? This is really, really hot stuff, okay? Pretty interesting planet, Venus. Okay. Let me sort of keep a track of where we are. Okay. Now, we're skipping Earth. Is that fair? Well, it kind of is, because next chapter we're going to focus on Earth and the Earth-Moon system. Okay, it's called the Earth in Space, but we're looking at the Earth and the Earth-Moon system. So that's why there's not much said about Earth here. However, the table that I was talking about here, that contains stuff about Earth as well. So do pay attention. I do want to point out a couple things about Earth before we move on. Remember we said the four inner planets were rocky planets. They're the densest planet. Most mass per unit volume. Okay? Which is the densest of all those planets? Not Mercury, not Venus, not Mars, Earth. Earth is the densest planet. Now, it's not too much denser than Venus. Venus is often called our sister planet, sometimes even called our twin, but there's really no comparison, okay? I was going to look at the density. We're 5.52 This is grams per cubic centimeters. Next densest is Mercury, 5.43, and then Venus is 5.25. So we're all right there really close. Surprisingly, Mars is much less dense than Mercury, Venus, or Earth, 3.95, but it's still much denser than any of the gas giants. Even though those are huge, huge planets, lots and lots of mass, they also have lots and lots of volume. Okay, so here we've gone to Mars. We went right past the Earth. Now, remember, Mercury, about 0.3 astronomical units from the sun. Okay, Venus, about 0.7. Okay, or 0.4, 0.7. Okay, Earth is 1. Mars, 1.5. So here, the distance between Earth and Mars is almost twice the distance between Venus and Earth. Okay? So Mars is way out there, 1.5 astronomical units. It's a fairly geologically active regions. At one time they were geologically active. Now they're mostly inactive volcanoes. Venus, they think, still has active volcanoes. We still have active volcanoes. Mars, mostly inactive, though at one time they were geologically active. They have canyons, which is a very interesting observation. What are canyons made from here on Earth? Any idea? What are canyons made from here on Earth? The Grand Canyon, any of your canyons, what are they made from?
Rock.
Water! Water moving through and eating away at the rock. Well, why in the world does Mars have canyons? Well, one possible explanation is maybe one time in its ancient past it actually had moving water, which then leads you to think, could it have sustained life? Because you certainly got to have water if you got life, okay? So, just the presence of water doesn't guarantee you had life, but it certainly is an indicator you could have. So canyons, maybe they were formed some other ways. I don't think so. They don't know of any other way. Now, there are what they call terraced plateaus near the poles, meaning they step up and down in terraces. I don't know if there's any explanation for why they're like that, but there are flat regions pitted with craters. Now, when you see that pitted with craters, what does that indicate to you? The very next bullet, thin atmosphere. There's nothing or not much there to stop the meteors from crashing into the surface. Okay? So, very thin atmosphere. And again, mostly CO2. Now, isn't that interesting, though? On the one side of us, Venus has an incredibly thick, dense atmosphere, mostly CO2. On the other side of us, Mars has a very thin atmosphere, but mostly CO2. We're stuck here in the middle. Our atmosphere has minuscule amounts of CO2. I would say less than 1%. However, every bit that it has there acts more like a greenhouse gas, so that's why we worry about it, okay? So why is the Earth different from our two closest planetary neighbors? I don't know. Our atmosphere, mostly nitrogen. Look at all the other planets. Mercury, no atmosphere. Venus, mostly CO2. Mars, mostly CO2. Jupiter, Saturn, Uranus, and Neptune, mostly hydrogen, helium, and methane. No nitrogen anywhere but where we are. Why? I don't know. Okay? Another issue. One of the reasons that we sustain life is because we have green plants, which are life. What are green plants doing all the time? They're taking CO2 out of the atmosphere, breathing in CO2. Their leaves have these openings called stomata, some on the bottom side, some on the top side of the leaves. They have those. Those are pulling carbon dioxide from the air, pulling water from the soil, and a few nutrients and stuff too. But then they're combining the carbon dioxide and water and forming carbohydrates, which the more complex they get, they form cellulose and other things that make up the plants. So the building blocks of plants are that carbon they're pulling out of carbon dioxide. That's why we can live, because our atmosphere, I think, if we didn't have green plants, it would still be mostly nitrogen, but number two would not be oxygen, it would be carbon dioxide. Because we do have plethora of green plants that's pulling the carbon dioxide out of the atmosphere, pumping oxygen back into the atmosphere, that enables us to live and breathe and exist. Thank you very much, green plants. Now, as I was hinting before, now comes a statement. Strong evidence for liquid water existing on Mars in the past seems to be out there. Strong evidence of that. Now, I'm trying to remember. All right, we go to 4:45 for class, and then from 4:45 to 6:15 is lab. Okay. Obviously, no lab today. We haven't finished the chapter. Okay, I got the lab ready, but it's not. We're nowhere close to finishing the chapter. Okay, so the green plants pull the carbon dioxide out of the atmosphere, provide us oxygen. Now we can breathe. Okay, if they weren't here, oxygen is so active it would combine with something and wouldn't be available for us to breathe. Thank you, plants. Okay. Now, we've skipped something else in between Mars and Jupiter. What was that? The asteroid belt. Now, what is the asteroid belt? It's a bunch of rocks, okay, flying around the terrestrial planets, Mercury, Venus, Earth, and Mars, but inside the gas giants, Jupiter, Saturn, Uranus, and Neptune. Okay? We're going to come back and talk about the asteroid belt later, but they're in between Mars and Jupiter. Okay. So, where is Jupiter? 5 astronomical units from the sun. So let's get this right. Here's the sun, okay? Then we have pretty close to it, about 0.38 to 4. There we have Mercury. Then 0.7, 0.72, we have Venus. Then we have Earth, 1 astronomical unit. Then 1.5, so half the distance from us to the sun, added to that, and you get Mars out there. Then you have the asteroid belt, okay? And then beyond that, 5 astronomical units. That's more than 3 times what it is from the sun to Mars, more than 3 times that before you get to Jupiter. That's 5 astronomical units, okay? Here's what speculation is. And again, this is speculation, but it really seems to fit. That perhaps there was the material there to form a planet, but they think that the huge gravitational force of Jupiter kept that planet from ever forming. And that's why it's a bunch of rocks out there in the asteroid belt. Maybe because Jupiter is by far the most massive planet. 318 times Earth's mass, okay? Remember, we're the densest, heaviest of the terrestrial planets, by far, and Jupiter, 318 times more massive than we are. Much bigger than that because they're gas, so they're, huge. mostly hydrogen and helium, but at the core is iron silicate core. Iron like we have at our core, silicates like we have on our surfaces. We'll talk about this in a couple chapters, what we mean by irons and iron silicates. Okay? So there's Jupiter. Now, does this seem a little strange to you? There's the sun. Remember, it's mostly hydrogen and helium. Then you have Mercury, no atmosphere. Then you have Venus with a heavy, dense carbon dioxide atmosphere. Then we have Earth with mostly nitrogen atmosphere. No other planet like that. Then we have Mars with a very thin atmosphere, but again, it's like Venus, mostly carbon dioxide. But then you get to Jupiter, back to being hydrogen and helium, like the sun. Now here's another speculation, a theory. Remember when everything was forming up? You know, the sun wasn't a stable star yet. It was a protostar. You were having explosions, nuclear reactions, all sorts of things were happening. Stuff was getting thrown out. Stuff was getting pulled in. The guess and understanding is some of those explosions probably blew all the hydrogen and helium beyond what became the asteroid belt. And that's why the gas giants are made up out of that. The innermost 4 planets, the terrestrial planets, have hardly any hydrogen or helium in their atmosphere. Now we have hydrogen, but it's usually combined with something else. Helium doesn't combine with anything. We have some, but nothing like the sun has and nothing like Jupiter and the other gas giants have. So the idea is most of that lighter gases got blown away way out there and then were packed together in the big planets. Okay? Jupiter being the biggest one. Okay. Now here's a picture. We're going to have to wait until the silly block gets out of the way. I can't do a thing to move this block. It's just in the way. There it goes. The Jupiter has an inner core, and it's a small inner core compared to the whole of Jupiter, but even that is 10 to 15 Earth masses. You could get 10 or 15 Earths inside the core of Jupiter, and it's mostly iron silicate core, which would be a lot like Earth is. But only 10 to 15 of us in there, okay? Then outside that, they have an interesting kind of phrase, liquid metallic hydrogen. That is a huge volume of that, liquid metallic hydrogen. Now, why liquid? Probably the pressure is forcing that gas to condense and form a liquid. The temperature isn't all that low, but you have that. Now, when it says metallic hydrogen, my interpretation of that to be lots of free electrons. I don't know if that's what they mean here. Dennis, I'm having trouble swallowing. I've talked too much. Let me get a swig of water. I may actually have to take a break and go clear my head. But let's see if we can continue. Maybe we'll do that right around the break time between class and lab, which we're not going to have a lab today. So next you have liquid metallic hydrogen. Then you have liquid hydrogen. Now why a liquid here? Well, my guess is because it's so stinking cold, okay? Because and pressure, which would tend to heat it up, but the pressure forces the molecules together, but also very cold, I would guess, because it's way out there, and that's about 20,000 kilometers thick, whereas liquid metallic hydrogen in here about 35,000 kilometers thick. And then it has an atmosphere, and again, the atmosphere is mostly hydrogen, helium, and interestingly enough, ammonia clouds. And that's about 500 kilometers thick. Now, what would that be in miles? Maybe about 300 miles thick of an atmosphere. Now, how do you tell the difference in the atmosphere and the surface? Well, they say the surface is mostly liquid hydrogen, so maybe the surface is liquid. But it's incredibly cold to be a liquid. Incredibly cold to be a liquid. And then the atmosphere, mostly hydrogen, helium, and ammonia. Now, why I said interesting on ammonia, ammonia is NH3. Well, N is nitrogen, which I always think of as the building block of every protein, which I would think meant life. But no, it doesn't mean life there. That's just how the nitrogen shows up there. Not as nitrogen gas like we have on our planet, but as ammonia gas like they have there. All right, now, more things about Jupiter. Jupiter, the largest planet, has an incredibly thick, probably pretty dense atmosphere. Look at these bands of Jupiter. This is a picture. These bands represent gases at different temperatures, basically. And in those bands, you have enormous storms going on. Some of them are light colored, some of them are dark colored. Okay? This one in particular is called the Great Red Spot. And if my memory's right, you can read in the book and check me up on this. The darker colors are, I think, the higher temperature storms. The lighter colors are the lower temperature storms. Let me see if I said that right. Jupiter, here we go. The Great Red Spot is near Jupiter's equator, not exactly, but close to it. It's a permanent, deep, red oval feature, some 40,000 kilometers. It's about 25,000 miles long in that length there, okay? It represents, has been identified by infrared observations to be a high-pressure region with higher and colder clouds. So the darker spots then, I guess, would be colder, the lighter spots warmer. I said it backwards, okay? This has been a storm that has been going on as long as we've ever watched Jupiter, and that's been hundreds, if not thousands of years. Yeah, probably thousands of years now. There's always been that Great Red Spot, one continuous, incredibly powerful storm. It does seem to be diminishing a little bit. So it may be getting a little bit smaller. So maybe the storm is dying down some. But it's one incredibly powerful storm. Okay. Now, there are some other things about Jupiter I think we're going to bring up later in the chapter. I can't remember where the slideshow brings it up, but I think the book brings it up later. But we'll get those. So I think the darker areas are the colder, isn't that what I just read? And the lighter areas are the hotter.
Okay, we can't hear you.
Okay. I've sort of faded out because I'm trying to find it in the book. The high pressure region, higher and colder clouds. I think the colder clouds show up dark colors. The warmer clouds show up lighter colors. Okay. Now here's something else that's fairly interesting about Jupiter. And part of it is the fact that it has these bands around it with these storms within the bands. Okay? Here's what happened. Remember before a guy named Copernicus? Most people thought the Earth was the center of the universe. Because think about it. It looks like the sun rises in the east, goes overhead, and sets in the west. It looks like the sun's moving around the earth. If you look at the stars, they all move. Polaris stays in the same position. I don't know how they explain that, but they all seem to be moving. Okay? The planets, sometimes you see Venus and Saturn, sometimes you don't. They're always moving. The moon moves. It goes through phases, but it seems to move around the earth, kind of. Okay? It does. It's the only thing that really does. So for the longest time, they thought the earth was the center of the universe. The planets didn't follow strict patterns. The moon had its own pattern. The stars and the sun had very definite patterns, but the planets were a pain. They sometimes would be moving fast around here, sometimes would slow down, sometimes would move backwards, and then turn around and move forwards again. Actually, the word planet meant wanderer. Okay. But they thought the earth was stationary and everything moving around it. Now, along came, I can't remember who it was that was credited with developing the first telescope, but it was sometime back about the same time period of Galileo, because Galileo heard about it and said, hey, I want one of those. Okay. Now that first telescope was not all that powerful. It was not all that reliable. It was just pretty weak, pretty lame. However, once Galileo, the great scientist he was, got his hands on the concept and started playing around with it, he came up with a telescope that was like 10 times more powerful than the one that was first discovered. And Galileo went out there and started looking into the sky. Whereas everybody had looked up there and seen what they thought were stars, though some of them were wandering stars, some of them were other things, he found out that, hey, wait a minute. He could tell the sun was really spinning. Okay? He looked and found Jupiter. And because of that great red spot and other features of Jupiter, he could tell Jupiter was spinning. And that led him to think, wait a minute. If all these other things are spinning, why isn't the Earth spinning? He wasn't the first to come up with that idea, but he was one of the more intriguing who did, because he jumped on Copernicus's bandwagon and said, yeah, that would explain everything. If the spinning of the Earth is what makes it look like the stars and the suns are going around it, then yeah, that would explain everything. The sun is the center, not of the universe, but of our solar system. It was the spinning of Jupiter. And the fact he could see that great red spot change position night to night, he knew it had to be spinning. And by the way, Jupiter spins pretty fast. Let's go back to our table. Whereas the Earth spins once every 24 hours. I'm not there yet. Mercury only spins once every 59 days. Venus spins backward only once every 243 days. Earth spins about once every 24 hours. Mars, just a little more than 24 hours. So it's a little bit longer day than Earth is, but not much. Jupiter, 9 hours to spin that huge planet one time. Whoa! It's spinning that fast and it's that big. No wonder there's all these storms on it, because everything's keeping that atmosphere all stirred up. It takes only about 9 hours for it to spin one complete revolution. Saturn, 10 hours. Uranus, 17 hours, but it spins backwards too, like Venus. And Neptune, about 16 hours. So while the Earth is the most rapidly spinning terrestrial planet, not by much, but by a little bit, all the gas giants are spinning much, much faster than Earth. We're 24 hours. They're on the neighborhood from 10 or 9 to 17 hours. Okay. So there's another thing about Jupiter. Okay? Okay, I know there's other things. Oh, here's a picture of the Great Red Spot. That's just a little bit of the Great Red Spot. Next to it is a pretty good sized white spot. Now, if this is really cool temperatures, this must be really hot temperatures. And if that were the case, the spinning is probably backwards from the other, because this atmosphere is very, very active. Okay? You know that by the fact that the planet is spinning so fast, it has such a large diameter, it has to be really twirling in space, which keeps the atmosphere all worked up, in my mind. Okay? Now, moving all over in the book. Jupiter. The way our book phrases it, it has tens of moons. Now, they could have got a little more precise than that. Like I was saying, my memory is something in the order of 50 moons. I can't tell where I've read it. It's obviously not this book. This book doesn't make a guess like that. But it does seem to be a whole bunch of them. Now, let's go back to Galileo. He saw Jupiter spinning, and that helped put him on the bandwagon with Copernicus. What else did he see? He saw going around Jupiter at least these 4 really big moons. Now, when I say really big compared to us, not really big compared to Jupiter. Jupiter is huge. These moons are relatively, they're large moons, but nothing close to the size of Jupiter. Now, they have names, and they're probably worth recognizing the name. I wouldn't try to memorize them. The first one, upper left corner here, that one I'm pretty sure is Europa. No, Io. Io is the first one here. Right here. This is Io. I-O. Pretty hard to spell, huh? The next one's Europa. Where that came from, I don't know. It looks like Europe, but it's not. The next is Ganymede, which appears here to be the largest, and then Callisto, which is almost the same size as Ganymede. Really large moons. Okay? Ganymede and Callisto, these two here, these 2 big moons here, are actually larger than Mercury. Actually larger than Mercury. Now, our moon, if I'm not mistaken, Io and Europa are about the size of Earth's moons. So these 2, Io being slightly larger than Europa, we're probably in between those 2 sizes in our moon. Now, what is unusual about that? The Earth, remember, is a relatively small planet. What are we doing with one of the larger moons in the solar system? Now, we're not as big as Ganymede and Callisto, probably not quite as big as Io, but we're bigger than Europa. And that's the 3rd largest moon in Jupiter, around Jupiter. So this is really sort of scary. What are we doing with such a big moon? Here's another theory. Speculation. Back, I'm just going to make a guess on this, about the same time that maybe Venus got hit with something really, really big that knocked it backwards in its spin? Wow. What if about that same time, Earth got hit with something really, really big, Now, this was a time when probably we were still molten. We were probably still hot from those explosions from the sun and radioactivity and everything else, that we were really, really hot from that, and we may have been molten. And if something really smacked us hard, it could have knocked a huge piece off of us. And that piece, they speculate, is the moon. Now, we'll talk about more reasons for that speculation now, but one is it's a way bigger moon than it ought to be, okay? No other planet has a moon nearly as close to the proportion of the planet as the Earth. See, the moon is about, I think, maybe 1/6 of that of the Earth, whereas even the biggest one here, yuck, I can't say the name, Ganymede. Sorry. Goodness, my eyes are just as dry as they can be. Though our moon's not nearly as big as Ganymede, but it's really big, Ganymede compared to Jupiter is tiny, okay? How do we have such a big moon compared to us? Remember I said Mars had 2 moons? They're tiny little moons, much smaller, and you know, Mars is much smaller than the Earth, well, their moons are even much, much smaller than Mars. So no other planet has a satellite, a moon, nearly as big as we do. So that's one reason they speculate maybe it used to be a part of the Earth and got bombed off. Okay. So they move on to Saturn. There's a few things about Jupiter that you probably need to know. Now, they're not going to say it here, but remember this is on page 389, okay? I'm going to show you the picture right there. There's one above it too. Okay, that's the picture. We're going to talk about it later in the chapter on the slide set because that's reflective of a comet. They're doing it here because that comet collided with Jupiter. So in an earlier edition, they put it with the comets. In this edition, they put it with Jupiter. So hang on to that. We'll come back and see that later. Okay? Let's move on to Saturn. What do you know about Saturn? If I say Saturn, what comes to mind? Rings of Saturn, of course. That makes Saturn probably the most beautiful of the planets, okay? Huge rings going around it. Multicolored, just incredible, okay? Now, so the rings, they're there. Here's a little hint. The Jupiter has some little rings. Uranus has little rings. Neptune has little rings. Saturn, though, has massive rings, okay? So all the gas giants do have rings. None of them are nearly as impressive as Saturn. Okay. Now, let's go back to our distances again. Here's the sun. Right close to that, about 3.38 or 4.4 astronomical units is Mercury. About 7/10 of an astronomical unit is Saturn. 1 astronomical unit is Earth. 1.5 astronomical units is Mars. 5 astronomical units is Jupiter, way out there. Saturn, the next closest planet, more than twice, or almost twice as far. 5 for Jupiter, almost 10 for Saturn. So what are they doing? They're almost doubling now. Not spaced like the early pictures are, almost doubling the distance from the sun. Not quite, but close. So Saturn is way out there. That picture we saw earlier looked like Saturn was right next to Jupiter. No, it isn't. It's almost as far from Jupiter as the sun is, Jupiter is from the sun. So Jupiter is almost halfway between the sun and Saturn. It's way out there. Now, here, besides the rings, which are certainly important, here to me is the most interesting thing, maybe after the rings, of Saturn. It's actually less dense than water. 0.7. That means if you had a pool of water big enough, which nobody does, and put Saturn in it, it would float. Okay? Saturn is less dense than water. The other gas giants are not. Most of the time, gases are less dense than liquids, not the gas giants. They're so tightly packed, they're dense. And they're liquid gases rather than being gaseous gases. You know, that doesn't make sense, but it's true. But guess what? Saturn is less dense than water. Their surface, we think, is very similar to Jupiter's, which would mean it's probably liquid, hydrogen, helium, and mostly liquid hydrogen, the atmosphere. It has 30 satellites. Now, its biggest satellite, its biggest moon, is Titan. Okay? It's the only moon we know about in the universe that has a significant atmosphere. Guess what, folks? Mercury doesn't even have an atmosphere. Titan does. And by the way, Titan is probably about the same size, in the same neighborhood as Ganymede and Callisto, so it may actually be bigger than Mercury. But it's the only moon with a substantial atmosphere. Okay? Pretty incredible. That's a picture, and I'm pretty sure this was taken from the Galileo probe. I think that's the one that took this picture of some of the rings of Saturn. Oh my goodness, how beautiful they are. We don't know exactly what they are, except they're dust, they're ice, they're a variety of substances. What gives them the different colors, I don't know, except they are made up of different materials. Why they're there more than the other planets, I don't know. It may be that just the low density of Saturn, this stuff just comes out the middle. I don't know. The other three gas giants are much denser than Saturn, so maybe they keep all their gases in. And they are around the equator type region, so that might be material that's escaping. I don't know. Okay. Now, in your book, there's a very interesting figure. I'm going to show it to you first, then I'll talk about it. Okay? That's Saturn. You can see its rings, and then you see other of its moons.
Okay, we can't hear you.
Okay, you see its rings. Okay, let me set it down. You see its rings there, and then you see some of its other satellites, some of its other moons around it. Okay? I wish I could show you the picture, but if you have your books, it's on page 390. Take a look at it. Okay? I'm trying to find Titan. Titan is way, way out there. Okay? And it's on one of the outer rings called the E ring. The ones we most notice are the inner rings, which is the D ring, the C ring, the B ring, the A ring, and then out from that is the G ring, and then way out there is the E ring, and that's where Titan is. Okay? It lists some of the other satellites or moons of Saturn. We know it has about 30, and that's why my guess is Jupiter has in the neighborhood of 50, 52, something around in there. That we know about. It may have more than that. We haven't discovered yet. Okay? And by the way, remember those 4 moons of Jupiter? They're called the Galilean moons because Galileo, with his more powerful telescope, he was the first one to see those moons. And that led him to believe then, too, if the moons are going around Jupiter, and our moon's going around us, why couldn't we be going around the sun? And sure enough, that supported the heliocentric model of the solar system. Okay. Yeah, the sun was the center. And I said it wrong. It was the Cassini-Huygens is probably the mission that took these pictures. They took incredible pictures. They saw more about Saturn than just about anybody else has. Okay, Cassini-Huygens. Now, I seem to have skipped, when we hit Mars, some of the, you see, we saw a figure on the space probes of Venus. They didn't show this in the book, so I'm just going to show it to you. It's in the text. There are some of the space probes of Mars. Okay. And when you look at that listing, you see the U.S. has more compared to what USSR. So Russia went to Venus, and the U.S. went a bit more to Mars. Russia went to Mars too, U.S. went to Venus too, but they just had different focuses, you might say, or foci. All right. Now, the Mars probes have gone much, we've sent them more recently. Remember, the Venus probes seemed, at least what was given in our book, or on the slide set, stopped about 1989. Well, since then, we've done, in our book, gives us two more, 2006 and 2007. Okay, and 2006 was a orbiting situation. It was the Venus Express, and the Messenger just was a flyby. It was just slingshotting off of Venus. But when you look at Mars, 1988, maybe half of the probes, maybe a few more than half, were done by then. Since then, 1996, 2001, 2003, 2004, 2006, 2008, 2012, 2014. Boy, we've kept going to Mars a lot more than we've kept going to Venus. Well, it's a bit more interesting. You can land something on Mars. We have some rovers on Mars right now measuring, taking samples and stuff. You can't do that to Venus. It's too hot. It's too inhospitable. Okay? So even though it's closer, you can't do nearly as what you can. You can't send data away from Venus. It's going to burn up. I mean, the equipment will burn up. Mars, no problem. Just keeping it running is the only issue. Okay? But there's not much atmosphere. There's not much acid. Nothing to stop it. It just has to get enough energy from the sun to keep the solar panels working. Okay. I forgot to mention that when we were there. Now, another thing I was going to mention, early on it was US, USSR, US, USSR, blah, blah, blah. Then suddenly here popped up ESA. Does anyone know what ESA stands for? European Space Agency. Now, the European Union kind of formed, but they also combined technologically to form a space agency. They didn't want to compete each country with the U.S. and Russia. They gathered together and did. And actually, some of the probes that they have done have been really, really interesting. So you might want to do a paper on that. That's another potential paper topic. Then you see down here in 2014, something really interesting. India sent a probe to Mars. Okay? So now we're not the only people in the space race. Europe's there, India's there. Japan has participated. They've sent up Japanese astronauts, but they usually done it with the U.S. or with Europe. Okay? Possibly with Russia, I don't know. There's a lot more in the text than we can possibly hit in the slide set. Please read the text. Okay? Now, we move further out. Okay? We go out to Uranus and Neptune. And poor things, they don't even get their own billing. They're lumped together. But think about this. Okay, here's our thing. Sun, Mercury, Venus, Earth, Mars, Jupiter, and then about twice as far as it is from Jupiter to, Moon, Earth, the Sun to Jupiter, you get to Venus. Saturn. Oh, I need to stop. Okay. Oh, let me see how the time is. I need to. Wow, I talked right past our break time. Okay, let's stop and let me call roll again. I'm required to call roll once for this and once for lab. Okay, Don's still not here, is he? Don Baldwin? Capri, are you still with us? It might be easier if I pull up the participants. We're down to 11 now. Let's see, Thomas is still here. Glad you're with us, Thomas. Valerie's still here. What a surprise, okay? All right. Caitlin's still here. Glad you're still with us, Caitlin. There you are. Cormisha's still here. Okay. Harry Seawright's still here. Good for you, Harry. Let's see, who else? Names are moving around on me. It's hard to follow. Jacob Walker's still here. Good deal. Okay. Leon Whitney's still here. Glad you're with us, Leon. Let's see who else. Nakaya's still here. I hope I said it right. Okay. Patrick's still here. See if I can find Patrick. There you are. Here's Patrick Robinson. Okay. Parisha's still here. There you are, right under Patrick. Okay. And let's see who else. Roy's still here. Way to go, Roy. And let's see, any others? Nope, that's it. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep, that's what I got. So if you see anyone else go or come, let me know so I can mark them for the second half. It's not half, but part of it. Let's take a brief break. I just need to get up and walk some. I don't know, my wife thinks it might be sciatica. I don't know. It seems like I have sort of pinching a nerve a little bit when I sit too long. I just can't stand it, and my knee hurts then and everything. When I get up and walk around, all the pain goes away. It's really bizarre. So let me pause Screencast-O-Matic now. I'll leave the Zoom up there, but let's take a very quick break. Try to keep it less than 5 minutes. I've got to go to the restroom and back. I hope most of y'all are back. I see some of you are still here. That's good. So here's Uranus and Neptune. Okay? Now starting to say this again. Here we are the Sun. Here's Mercury, about less than 4/10 of an astronomical unit from the Sun. Then about 7/10 we have Venus. At 1 astronomical unit we have the Earth. 1.5 astronomical units we have Mars. 5 astronomical units we have Jupiter. Almost double that, 9.5 we have Saturn. And almost double that we have Uranus, 19. In fact, that is exactly double that, and it's approximate. And then not quite double, again, you get Neptune. Way, way, way out there, okay? Now these two are the outermost giant planets, it's often called gas giants. They are very similar internal structures to each other. They're basically very close to the same size. Lots of things very similar between the two of them, okay? Very similar, amazingly so. Talk about twins. except there are some differences too. One of those differences, Uranus, all the other planets basically have their axis of rotation is pretty much perpendicular from what the ecliptic plane is, okay? We are tilted a little bit. Most of them are tilted a little bit. Uranus spins almost like this. Its axis is almost in the ecliptic plane. It's on its side, and nobody knows why. Maybe it got hit, but it's way out there. Why would it have gotten hit? We don't know, okay? We just don't know, okay? It also spins backwards, but it's sort of hard to tell because it's laying sideways, but it is spinning in the opposite direction from what it should. So it and Venus spin backwards. It's the only one that lies on its side, you might say. Neptune, just out there. We know probably the least about Neptune because it's so incredibly far away, okay? Now, some of the things in the book I think you would find pretty interesting. I haven't hit them all. I wish they spelled it out a little bit more, but the there's not much to say about these. We're learning more about them all the time. And here's another speculation thing, and this is purely speculation. Neptune is so stinking far out there. It would be good to someone do a paper and say when it was even discovered and how was it discovered. I'm not sure I'm sure something has, they've sent satellites out there. But you see, if you think about, and this is what I wish they would have been a little more explicit on. If it takes us months, sometimes years, to get a probe from here to Mars, certainly months. To go from here to Saturn is years. To go from here to Uranus would be multiple that of Saturn, many times multiple. Neptune, you're basically talking decades, okay? So, my goodness, do we have technology to power things? Now, it doesn't take a lot of power to do because you're so far from the gravitational pull of the sun, but still, that's a long way, okay? And everything has to keep working for that long. And it can't run into any space junk, to damage anything. And if you did, you're lost. So it's an incredible length of time for us to send something from here to Neptune. So we haven't, and what we sent was so many years ago, the technology was pretty poor back then. So to get something more recent, we're going to have to send, but it'll be old technology by the time it gets there. So it's a pretty unusual situation, okay? That's sort of what I wanted to say about why we know so little. Now, here's the speculation part. And I don't think the book goes into this much, but there is a lot of speculation now. Roy has come back. Evidently, he had to leave, so he's come back. I think I'd already marked him here. Yes, I did. Okay. So, there is a certain amount of speculation that, like I said, we've hardly seen Neptune. We have sent some satellites close enough to take pictures, so we know it's there. We know it's there from its gravitational pull. We know it's there. Good telescopes can see it. Really good telescopes can see it. But there seems to be something beyond it. Now, if everything was almost doubling in distances by the time you got to another planet, you're going to be talking something on the neighborhood of 50 to 60 astronomical units away. And if you're looking at something that far, the light reflecting off the sun is going to be so dim, you'll never see it, okay? But we may be here and it may be somewhere here, and the odds of being close enough to detect it are really bad, okay? Even if we're on the same side of the sun, it would be really bad. But there does seem to be enough gravitational uncertainty there. There seems like there is another big body out there somewhere. Could be there are 9 planets or more. It's just Pluto is not the 9th one. Okay. So, I think I've beat that to death. Let's move on. I can't move on until I hit this. Okay. Oh, and here's a picture. And this picture, I'm trying to recall, I'm pretty sure this one is Uranus. Not certain, but I believe it is. And the difference, they've set this aright. The one that's in the books is a little bit better because you can see then that its axis is perpendicular to where it ought to be. Because it does, like I said, all the gas giants do have small rings. It has a ring around it. Not around the collar, but around it, okay? Now, the other source for some of our pictures of these, I forgot to mention, is the Hubble Space Telescope. That is so big and massive, and it has no interference with the Earth's atmosphere because it's outside most of that they can take some much better pictures with it than you can with other things. So some of these are from Hubble Space Telescope too. Okay, let's see if they also show Neptune. No, they don't. Okay. So now we're moving, the book has a picture of Neptune. In fact, I think maybe this edition, the 8th edition, they hadn't gotten this picture from that. Anyway, now we're moving to 15.2, smaller bodies of the solar system. Okay? Now, what are these smaller bodies? They are comets. They are asteroids. Now, the comets mostly are way out there. Asteroids are in between Mars and Jupiter. So they're inside about where we are. Okay? Now here, this is wrong. I think they should have written this as meteoroids. We're going to see that a little later. Don't read this as meteorites. Read it as meteoroids. These are just other pieces of stuff floating around out there. They could be moving, whatever. Meteoroids. Meteorites only when it hits the Earth's surface. They're no longer floating around out there. They're on the Earth's surface. So these should be meteoroids. Okay, what is all this stuff from? Well, they think it's left over from the solar and planetary formation. Now, we talked about stellar formation in the last chapter. We're going to talk about planetary formation coming up in this one. Here they talk about it now without explaining. But remember, this was part of the protostar to star phase when things were exploding, coming together, radioactive effect, all sorts of things were going. Some things clumped together to form planets, okay? Sometimes with little pieces floating around them which made their moons. Some things didn't clump together well, that formed the asteroid belt. The rest of it was just left out there somewhere. Now, these are incredibly small bodies, most of them, okay? But there's so many of them out there. This is a statement, and this is the one that I said is misleading. The mass of the smaller bodies, that's all the comets, all the asteroids, all the meteorites added together, the mass of the smaller bodies may be 2/3 the total mass of the solar system mass. They left off one thing here. Exclusive of the sun. The sun is 700 times more massive than all of it put together. So they couldn't be 2/3 of the total solar system mass if you included the sun. But excluding the sun, there's more mass of these smaller bodies than there is all the planets, all their moons, all that kind of stuff. I don't know where they're counting the Maybe the moons are counted here, but still. Now, these smaller objects sometimes bombard the larger object. And this was the figure I was talking about in the book, is back there with Jupiter, and the slide set is here, because it sort of makes sense here. Here is a comet. They used to have a name, the Schumacher-Levy comet. I guess it was first identified by these two people, and they gave it both names, Schumacher and Levy. It was number 9 that they did, Schumacher-Levy 9. It got too close to Jupiter, and you don't do that. If you get too close to Jupiter, Jupiter's going to suck you in, because Jupiter has an enormous, enormous gravitational pull. It pulled it apart. I'm sorry, Schumacher-Levy was the name of the comet. It produced at least 9 big fragments. First, Jupiter ripped it apart, and then the fragments hit the surface. I don't know if I can count them off the way they do. That looks like 1, 2, 3, 4, 5, 6, 7, 8. It looks like more than 9. But anyway, those fragments hit the surface of Jupiter and left spots there that you could see for a while. Why spots? Well, going through that atmosphere, they got really, really hot. And that's formed these spots on Jupiter. Now, you might say, how did they know this? Did some professional astronomer that was spent all of his time watching Jupiter happen to see this happen? No, it wasn't like that at all. It was an amateur astronomer. This guy who just had probably a pretty good, but average to good telescope, just liked looking at the things. He knew where the things were out there, including he knew where Jupiter was. And he just happened to look at Jupiter this one night and said, wait a minute, what are those spots? They weren't there the last time I looked, and I know I'm in the same part of Jupiter. What's going on here? So he reported this probably to his local affiliate of the IAU, International Astronomical Union, and said, what's going on here? They said, what are you talking about? He gave them the sort of the coordinates and stuff. They went out and looked, and they said, uh-oh, yeah. And they started doing calculations, and sure enough, shortly before he saw these spots, that was about the time that Schumacher-Levy, the comet, was on its normal route to come in and go around the sun. It never made it. Jupiter pulled it apart, and the pieces at different times crashed into the surface of Jupiter. But an amateur astronomer saw it first. Okay? 1994. Okay, we've been talking about comets. What are comets? Okay? Well, there are a variety of things, and they live in 2 basic places. The first of these is called the Oort cloud. Okay? Now, we're going to see a picture a little bit later. I'm not sure it's on the slide set, but I'll show it to you. The Oort cloud is out there. I mean, way out there. This is the place that's the origin for your long period comets. Those are the comets that come in and go around the sun and go back out, and it takes more than 200 years for them to do it. Some of them way more than 200 years. Now, where are they located? They're located anywhere from 30 astronomical units, which is right around where Neptune was, all the way out to a light year away. Now, they don't give me a good conversion between how much that is, but it's quite a distance. So, believe it or not, the sun, that massive, but it's only an average-sized star, in the center of our solar system, has the effect that it keeps things 1 light year away in its gravitational reach. And it's an average-sized star. This is amazing. Okay? Now, there's another band or belt called the Kuiper belt. Now, I'm not sure that's the correct pronunciation. I think I've read or seen or heard someone say the Kuiper belt. But I think Kuiper is easier to say, so I'm going to say Kuiper belt. actually heard one person call it the Cupidor belt. I say, wait a minute, have I misspelled it? No, she was mispronouncing it. So it's the Kuiper or Kuiper belt. It's the origin for shorter period comets. Those are those less than 200 years. Now, one of the most famous comets around the Earth that we've seen occasionally has been Halley's Comet. Halley's Comet has a period of about 70 years. And the last time it was close enough to the Earth that you could see it, but you had to strain to see it, was back about 1985, I think it was. So somewhere around 70 years from there, which would be about 2055 or so, I think it may be coming back again. Now, that last time, it was not very visible at all, okay? The time before that, which would have been about 1910, around in that time period, it was much more visible. It created quite a stir. The time before that, when it came through, or one of the times that it came through before, it was so spectacular, a lot of people thought the end of the world is here. Okay, suddenly this huge bright light was in the sky at night. Yeah, I think you could sometimes even see it some in the daytime, but it was sort of bleached out by the sun. But at night it was very, very visible. And there were those who speculated it was the end of the Earth. You know, that was our time was up. But it turned out just being a comet. But that's been the one most frequently seen and most vividly seen. There are others, but usually you have to know where to look and have pretty powerful instruments to see them. The trouble is, and we'll get to this later, but anyway, the Kuiper belt, let me go back here. Halley's Comet would be in the Kuiper belt, and probably Schumacher-Levy was there too. It's sort of a disc-shaped region that goes from 30 to 100 astronomical units from the sun. So the Oort cloud and the Kuiper belt both are between 30 and 100 astronomical units, but the Oort cloud goes way, way further. Now the difference is the Oort cloud is a spherical cloud. It's all the way around. The Kuiper belt is just sort of like the solar system. Everything's within one plane pretty much. It's just a little bit further out there. Okay? Now, what gets the comets to come in? Something does. Some sort of gravitational nudge, and here they come in toward the sun. Now, it may take, like we said, 200 more years for them to make one rotation, or it may take as few as 70 years to make a rotation. But it's a long, long time for them to go in and come out. Now, their orbits are very, very elliptical, meaning most of the time they're way out there, other times they're in fairly close, like between us and the sun, really close, okay? And some sort of gravitational nudge makes them start coming in, okay? But they don't come in some of them are pretty regular, but others are more irregular, okay? Now, here's the picture I was talking about, okay? Now, this is kind of hard to fathom, but you see this little bitty bit in the center here? There's the sun, and there's all the solar system. This is the orbit of Uranus. That's the orbit of Neptune. There's the orbit of Pluto. You see, it's not on the same plane. It's really elliptical. It's out of shape, out of whack. All that from the farthest of Neptune and Pluto, it's right in the center there. Okay? The Kuiper belt goes out from here and here. That's the Kuiper belt. I don't know exactly where it's considered to end. It's still sort of a disc-shaped region that kind of mirrors where the planets are and stuff, only way further out there. From the outside part of of Neptune all the way out to 3 times that far. Okay, so there would be the Kuiper belt, if I can get my cursor back, somewhere in this region here. The Oort cloud, I mean, it's way, way, way out there. This is 50,000 astronomical units. This is here. This is 50 astronomical units there. So this is 1,000 times bigger than this. Okay? So you're talking enormous. And that's why they can say that 2/3 of the solar system mass, not counting the sun, but 2/3 of that solar system mass could be in these smaller bodies. Look how many there are. Goodness gracious. There's got to be billions and billions of them out there. They're all very small, but add all that mass together, and that really dwarfs. 1/3 of the mass is in here, and 2/3 of the mass is out here. That's understandable. That really is. Now the sun, 700 times more massive than all the rest of this put together. So that's the big thing in the pot. And again, that's probably a bad illustration there because it's way, way more massive than that. Okay? Does that kind of make sense? Okay. Now, what are comets made of? Well, they're small solid objects. Okay? One of the descriptions of them, they're a dirty snowball. Okay? Now, why a snowball? Well, it could be frozen water, so it's actually ice, but it also could be solid carbon dioxide. Does anyone know what a common name for solid carbon dioxide is?
Dry ice.
Dry ice, you're absolutely right. Okay? Very, very cold. It could be frozen ammonia or frozen methane. You see, they're way, 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 way out there, so all these things would be in solid form, not normal gas form. Water is normally liquid, but it can be gaseous. Carbon dioxide, ammonia, and methane are usually gases. They would be solid. Okay, that's the snowball part, the frozen stuff, but also mixed in with that is the dirty part. That's the dusty or rocky bits that are mixed up in there. Okay, now that, especially the rocky bits, that's going to be of interest to us later. So hang on to that notion, dusty or rocky bits. Also in the fact that those dusty and rocky bits are held in the frozen part, which is normally liquids and gases, but they're frozen, so they're in there. Okay, now the comet also has a head. I wish I could get my cursor to, there it is. Okay, a head. That's sort of the most part of the dirty snowball. A solid nucleus, but then the nucleus is sort of surrounded but also trailed by a coma of gas. Now that's an interesting concept. Here's a picture of that. The head is somewhere in here. That's your dirty snowball. That's the solid, frozen gases, liquids, and rocky bits and dust all frozen and mixed in there together. What the coma is, there are 2 types of these tails. One is ionized gases. Some of these gases, especially as they're getting closer to the sun, they're picking up radiation because there's a lot of radiation out there in space. That's not matter, but it's radiation, radiant energy, big amounts of energy. That can be knocking electrons off of these gases and making ions. And those ions, if they're of such nature they give off light, like in a fluorescent tube, that's exactly what's giving off light in the fluorescent tube is ionized gases. Well, pretty much. Okay? Now, that's one thing. The other thing that could be is the dusty parts. I wish this box would go away. It fades out in a minute. But I have to wait for it to go away. Go away, box. Get out of there. Okay, there it goes. That could be the dusty parts. Well, where's the dust coming from? Well, as this dirty snowball, which is made up of frozen water and these frozen gases, as it gets closer to the sun, it also heats up. When it heats up, it starts either melting or subliming, so some of that dust and rocky bits that were part of it now are freed. So now there is dust out here. Well, as it gets closer to the sun, either the gases are ionized or the dust and rocky pieces reflect light from the sun. So that's where the two types of tails. Hard to say which is which. It sometimes could have both. Here is the thing. The tail always points away from the sun. The sun is in this direction here. The head is always pointing toward the sun. Now, which way do you think this comet's moving? Is it moving the way I was just moving here, or is it moving this way, or some other way? You cannot tell. All you can tell is which direction the sun is. Even if this comet's moving away from the sun, the nucleus or the head is always pointed toward the sun, and the tail is always pointing away. Even if this comet was taking off in this direction, it still looked just like this. This is not stuff being left behind. The coma is now leading it, okay? Because the head always points toward the sun. The solid nucleus points toward the sun, the comet head, and the tail always points away. So you can't tell which way it's going just by looking at it. And which comet this was, I'm not sure. They don't indicate here which one it was. The one that's in your text, do they give a name of that one? No, they don't, okay? It has a picture of one, but it doesn't give a name. So whatever comet it was. Observations by the Vega and the Jati spacecrafts found the nucleus of Halley's Comet to be an elongated mass of about 8 by 11 kilometers, that's 5 by 7 miles, with an overall density less than 1/4 that. Yes.
We can't hear you.
Oh, I'm sorry. I'm turning to read the book. Okay.
You just showing that you're present in the class.
What's that again?
So when you gonna do it at your own leisure?
I can't understand you. Sorry. What'd you say? Okay. Whoever was speaking ill of HP of HP computers, I'll add this to it. I think they. Okay, some of y'all have some great microphones, by the way.
Phone's not muted.
I don't know if you know they're activated, but some of them are, because we're hearing just regular conversation. Let me say this about this microphone. The old computer I had, the old Fujitsu, probably, excuse me, someone has a microphone on, and you're not, it doesn't sound like you're participating in class, are you? Or if you are, please speak a little more clearly. But it doesn't sound like you are. Did someone have something to say? Please speak. I mean, I don't want you not to speak unless you're not talking about something in class. Okay, I was saying that the old Fujitsu that I had, I could be anywhere in the room and still be, not anywhere in the room, but between the room and the board, facing the board or whatever. Yeah, I would fade out, but still people could hear me. But this one, I have to be facing directly at the microphone in order for you to hear. If I hold up a piece of paper, sometimes it keeps people from hearing. That's not right. This is a really weak microphone, and we tried, my wife came up and tried to do something to improve it. We couldn't find anything that would make it any better. But here's what I was saying. Observations, this is on page 393 in the left-hand column. Observations by the Vega and Jato, I'm sorry about that, spacecrafts found that the nucleus of Halley's Comet to be an elongated mass of about 8 by 11 kilometers, that would be about 5 by 7 miles, with an overall density less than 1/4 the density of solid water ice. So it's a really low density thing. As the comet nucleus moved toward the sun, it warms increasingly intensely with solar radiation, and somewhere between Jupiter and Mars, the ice and the frozen gases begin to vaporize, releasing both grains of dust and evaporated ices and those rocky pieces. And these materials form the large, hazy head around the comet called the coma, and then the tail that grows out of that. Okay, so what the purpose of saying that was, or reading that to you, every time it comes in, it has to be losing part of its mass, because once that ice and those dust particles start leaving it, there's no way to get them back again. So therefore, maybe that's why Halley's Comet was much less visible last time than it was the previous few times that it came around. So some of these comets may come and go, mostly going, So anyway, that's comet structure. Let's move now to asteroids. Okay? Again, we've mentioned, sorry, I can hardly talk. Let me get another swig of water. We've mentioned several times the asteroid belt is located in a belt between Mars and Jupiter. And remember, there's a huge difference between Mars and Jupiter. Mars was 1.5 astronomical units, Jupiter 5. Easily, you could have fit another planet in there. And they think maybe it was. Should have been, anyway. The sizes are up to 1,000 kilometers. I'm assuming that's a diameter, which would be about 600 miles, which is really pretty big. And some of those would be classified, I think, dwarf planets. They varied composition. The inner belt are stony, which is not surprising because that's where the terrestrial planets or the stony planets are. The outer belt, dark with carbon. Now, why that, I don't know, unless the carbon is stuck on ice or something like that. Others are mixtures of iron and nickel. That's interesting. That's what the interior of the Earth is. Mostly iron and nickel. We'll see that a little bit later in a few chapters from now. They feel like the asteroids were formed from the original solar nebula, but, and here's the theory, prevented from clumping by Jupiter's being strong gravitational field so close by that it prevented them from clumping together like the other planets did. Now, here's one of my theories, and I think other people, I don't think I'm original with this. Why does Jupiter have so many moons? I bet you it's yanked asteroids out of the asteroid belt and started them circulating around itself. I wouldn't be surprised if that's where a lot of Jupiter's moons come from. They've ripped them out of the asteroid belt, any that were flying a little too far away. Okay, so here is the illustration of that. Here's the sun. Somewhere in here would be Mercury. Somewhere in here would be Venus. Somewhere in here would be Earth. Then Mars is out here at 1.5 astronomical units. Jupiter out here at 5 astronomical units. The asteroid belt is basically between 4/10 the distance between the sun and Jupiter to 6/10 between the sun and Jupiter, which makes it on average right around halfway between the sun and Jupiter. And remember, the planet. Sorry? Okay, are you talking to me or someone else? Okay. Which would make it, if you remember, from Jupiter to Saturn, about twice the distance. From Saturn to Uranus, about twice the distance. From Uranus and Neptune, not quite twice the distance. Well, guess what? This would be half the distance from Sun to Jupiter. That would be here. That would fit perfectly for another planet to be right in here. But big old bully Jupiter must have kept it from happening. That's the theory anyway. Okay? Now, that wasn't much on asteroids, was it? They kind of moved right on past it. Let's see if we can get a little bit more about it. In your text, on page 395, if you got your book, there is a picture, a close-up photo of an asteroid taken from the spacecraft Dawn in 2011, and it looks like you see big old craters there, and those three big ones sort of to the left and in the curvature there, they make it look like a snowman. So they call this the snowman asteroid because it has those. But you see, asteroids have no atmosphere, so therefore they get bombarded with meteoroids also, other things flying around out there hitting them. And you could easily imagine something big enough to make that big of a crater probably knocked it a little further one way or another, and that may lead to it getting out of orbit. And if it knocked it toward Jupiter, Jupiter's going to pick it up, okay? If it knocked it toward the sun, it may actually become then a meteoroid, okay, which we're going to get to in just a minute. Okay. I'm looking for something in the book that's not in the slide set. At least I think I'm right on this. Maybe it's still coming up, so let's just wait and see if it comes up later. Okay, let's move on to meteors and meteorites. Really, it should have started with meteoroids. Okay, now what is a meteoroid? Okay, now remember this. Those comets, when they come in from way out there, they could be pretty big. They're masses of dirty snowballs, with gases or liquids that have frozen and then containing rocks and dust and other things. As they come into the sun, the solar radiation starts melting some of those gases or subliming some of those gases, releasing some of those rocks and dust as the comet comes through. And the closer it gets to the sun, the more they're released. And then finally it makes its way out and goes back out. Now maybe it runs into other things and collects a little more mass on the way out. I don't know. But that leaves all this space junk. Rocks, dust, other things that are just floating there in our solar system. Okay. Those are meteoroids. Those rocks, remnants of comets, or asteroids that may have gotten bumped around some by other objects, okay? The remnants there are meteoroids. They're just floating around out there. What a meteor is when a meteoroid encounters the Earth's atmosphere, and when that happens, then it starts heating up, because our Earth's atmosphere, even though you don't think air has much mass, it does, and it has friction because these things are going at very high rates of speed. The next chapter will talk about some of these rates of speed. The Earth is flying through space at high rates of speed, whams into some of these things, and with those kinds of speeds involved, even in the Earth's atmosphere, it's going to create a lot of heat. So that's what a meteor is. When the meteoroid, which is just a piece of rock or object out there, actually hits the Earth's atmosphere and starts burning up. And that's what makes it produce light. The heat from that produces light. The meteor showers happen, that's sort of a nickname, when the Earth passes through the tail of a comet where the comet used to be and dropped off all those pieces. When we pass through that, that's when we have the meteor showers. And we'll talk about when those are and when you might be able to see them. Now, that's a meteoroid when it's out there in space. Meteor when it hits the Earth's atmosphere. If it makes it all the way through the Earth's atmosphere without burning up completely, that makes it a meteorite. So that's why that was the wrong term to use way back there. It's not a meteorite until it hits the Earth. So a meteoroid surviving through the Earth's atmosphere to strike the Earth's surface. Now there are several kinds that have been discovered. Iron meteorites, stony meteorites, and there's two types of those, and then you have stony iron meteorites. Okay? Now, these two types of stony meteorites are either chondrites or achondrites. Now, what a chondrite is that stony, usually siliceous material, silicas or whatever, that obviously at some point in its past has gotten so hot that it melted, but then when it cooled, it became little spheres. Okay? Your book describes this. Let me get it over here in front of me so I don't fade out on you. Okay, I hear a phone ringing. It's just going to have to ring. My wife's not home. She had to go in the office today. Okay. On page 396, the left-hand column, okay, the stony meteorites are further subdivided into two groups according to their structure, chondrites and achondrites. Chondrites have a structure of small spherical silicate minerals or glass that have obviously melted before and then re-solidified as little spheres. Okay? And they're held together by a fine-grained cement, and we'll talk about that in a later chapter too. But anyway, those are chondrules. If they do not have those chondrules, those little spheres, then they're called achondrites. Okay? Chondrites if they have the chondrules, and achondrites if they don't. Okay? So, the iron, that's like is in the interior of the earth. Okay? Iron is the prominent mineral in the interior of the earth. Stony, remember they said siliceous material, silicates, that's the surface of the earth. Okay? And stony iron would then be some sort of an intergrade in between the two. So basically, this is why they say they're remnants of, and earlier we said the small bodies are remnants of the early formation of the planetary system that we have. These are pieces that didn't get yanked together. Okay? So that's, okay. Here is the meteor showers. These are when we pass through the tail of a comet. Okay, we had one back in January the 3rd, about one every 2 minutes. If it's a clear night, not too bright, out in the country somewhere, you might see a meteor every 2 minutes. Okay? And that was, there is a constellation called Quadrant or something like that. I don't know that one. Aquarius, one passed through that about May 4th, so that's already passed. The next one coming up, and this is one of the bigger ones, through the constellation Perseus. I don't recall that showing up on our calendar, on our star map, but go and look and see if you can find Perseus. That's where the most of the meteorites would be then. That's August 12th. Now, we'll already be out of school from this term, but go out and look. You'll see more than one every 2 minutes, okay? If it's a clear night, not too well moonlit, and you're not in too much light pollution, go out in the country, see if you can see it. Orion, which is my favorite constellation, it's the easiest one for me to pick out. Not as easy as the Big Dipper, but Big Dipper's not a constellation. October 22nd, that's about one every 4 minutes, okay? Taurid, that would be Taurus the bull, that would be first on November 1st, and then on the 16th, we pass where it comes in and where it went out, the tail of whatever the comet was then. But then it's about one every 12 minutes. I'm not sure I'm going to stay out there long enough to wait and see. Well, I missed it that 12 minutes. Let me wait another 12 minutes. Same thing with the one in Leo, the Lion, November 17th, the night after the second Taurid. But Gemini, however you say that, December 12th, almost one a minute. If it's a clear night and not too well moonlit, and you're out in the country somewhere, and it's not too cold, go out there at night, December 12th. And you can go to places like that star count. I found that just out on the internet, star map, something like that. Birmingham Astronomical Society, anything like that will have information on when you might see some of these meteor showers or other things that are interesting astronomically. Okay. Any questions about meteors, roids, meteors, or meteorites? Okay. Now, there is a picture in the book, and to me, it's sort of a almost contradictory kind of picture. There it is. I'll just show it to you, and then let's talk about it. This is on page 396, and it shows the top one up there was a stony meteorite, and the smooth black surface was melted by compression of the atmosphere. The B one, the one beneath that, was a iron meteorite cut and polished, etched with acid. It makes it look like the iron meteorite is lighter in color than the stony. They're usually reverse of that. That's where you etched it with acid. So that's what made the color contradict. Okay? And then you can read the rest of it. The other part of it was a time-delayed photograph of a meteor shower. And you can actually see them streaking across the sky. They didn't happen all at once. Because you left the aperture open, you got all that showing up there. Okay. Now, I think that does it for meteors and meteorites and meteoroids. Oh, here we go. Here is the one they call the stony meteorite. It looks really dark. Then the iron meteorite looks much lighter. But that's confusing. The stony meteorite usually is not as dark as this one, but they etched this with acid. I don't know why, but to show contrast, I don't know why. These are, they have them right, but it's backwards from what you would think. Usually the iron meteorites are darker than the stony meteorites. The stony meteorites are usually pretty dark too, because they picked up carbon or whatever. Okay. This one, though, they've etched, so that's what makes it look so white colored. Why they do that, I'm not sure. All right, now we're moving to 15.3, origin of the solar system. Okay, so we're going back to the origin of a star. Okay, and remember, before it was a star, okay, early on it was just a mass of gases, a nebula. Okay, after that, some sort of disturbance, perturbation, something made it start collapsing on itself, and when it got hot enough to support nuclear fusion, then it becomes a protostar. Okay, it's not turning back again to be a mass of gases. It's going to be a star. So the protostar was the step. After that, it's going to be a star. Well, about the same time that was happening, you have the protoplanet nebular model. So when the star is beginning to form and nuclear explosions are pushing things out, gravity is pulling it back in, you have a lot of mess going on. And with that mess, and this is what they call stage A, let's see if we can find it up there. Here's stage A. Everything's hot. The formation of heavy elements in many earlier stars and supernovas are grouped together. Some of these are radioactive, some may not be, but anyway, it's all a hot ball of whatever, okay? The nuclear explosions are happening, radiation's happening. You get the centralized part here that's going to be your star, and then you have the plane around there, And this is all has to do with the physics of rotation. You know, when things rotate, they tend to elongate in the middle, okay? And this is happening because this is rotating pretty fast, and that forms the protoplanet nebular model. This is still a mass of gases, but this is where the planets are going to group together. That's where the star in the center, our sun, is grouping together, and this is where the planets and some of their moons, our asteroids, and other things are happening. Now, way out here is where the comets are. Those are things that have been just thrown out there. Anytime you spin stuff, you have stuff scattering in all directions. That's going to be later the comets. Okay, so there's stage A. Formation of heavy elements in many early stars as supernova. They came from that. The concentration in one region of space as dust, gas, and chemical compounds. That's what you see here. Center of that will be our star or our sun, and around that will be the planetary disk, which is going to ultimately form the planets. Okay, so here's stage B, the formation of large rotating nebula. Okay, and you see these are masses of gases rotating around what is finally sort of settled out with dynamic equilibrium to be the star or our sun. Now this is probably way too small, okay, but they didn't want to overwhelm it. So you still have masses of gases. So that's why it's called a rotating nebula, large rotating nebula. The gravitational contraction, the spin rate increases, and now these are going around faster, and the masses of gases may be grouping together, may be spreading apart. Most of the mass concentrations are in the central protostar. That's what they're showing here. I've already said that. The remaining material forms what they call the accretion disk. Now here was the early stages of that. Here are the later stages of that. You have masses that tend to stick together going around there, but they're still nebula. They're still masses of gases. They're still that hot. The material in the accretion disk began clumping. Mercury clumped there, Venus clumped there, Earth clumped here, Mars clumped there. The asteroids would have clumped, but way out there was Jupiter, which kept it from clumping. Or that's the theory anyway. Okay, and then the gas giants clumped further out. Now further out, that's where when these explosions were happening here, the gases got thrown further and further out. And that's why the gas giants are out there and the heavier rocky planets are in the interior. That's my theory anyway. Okay, stage C, that's what we get down here. It's underneath this ugly block. Hopefully that will go away soon. The protosun becomes a star. It was a protostar, it becomes a star. Protosun becoming a sun. The solar ignition flare-ups may have blown away the hydrogen and helium atmospheres from the inner planets. In the process of forming a star, you have all these explosions that go on every now and then, probably blew the lighter gases, helium and hydrogen, way out to the outer regions where later they formed the gas giants. The heavier stuff, like the rocky, iron, nickel, other heavy elements, they stayed in the planets, the terrestrial planets. Those were in here. Okay? The protoplanets heated, separating heavy and light materials. Okay? Now they're called protoplanets. The protosun has become a star, but these are still not yet planets, protoplanets in the process. They're still heating up, probably radioactivity and just collisions, whatever. The larger bodies cooled slower, with the heavier material settling over longer periods of time into the central cores. And that's why the cores were sometimes iron, nickel, stony materials, even in the gas giants, because it still had stuff thrown out there. Okay? But this is now when they are in stage C. almost planets now. And that represents the inner one there, Mercury, a little one, then Venus, then Earth, and then a small Mars out there. Okay. Now, here are some of those ideas about the solar system. This actually is 15.4. The first three sections, two sections, very long.
We can't hear you, I'm sorry.
Okay, I was facing the camera, but I'm not directly in front of it. I moved over just a little bit just to stretch. Again, my hip tightens up on me every now and then. So here's the ideas about the solar system. This is on page 398, right-hand column, 15.4. Well, we now have what we call, the earlier ideas was the geocentric model. Geo meaning Earth, centric meaning Earth being the center of the solar system, or they thought the universe. The attempt by some of the early Greek astronomers and philosophers to explain the observed motions of the sun, the moon, the stars, all seemed to be going around the Earth. They thought the Earth was the middle. The problem was the sun went at one rate, the moon went at a different rate, the stars went at a fairly uniform but different rate, and then the planets, oh my goodness, they just messed up everything. Okay? They tended to go in a pattern, but that was a weird pattern. This placed the Earth in the center of the orbits of all the planets, all the stars, the sun, the moon, everything. Those planets, though, were a pain in the neck. So exceptions of this model were explained by a guy named Ptolemy. And so this got the name the Ptolemaic system. He had some really complex, convoluted way mathematically of explaining why the planets didn't quite fit, and also why the sun and the moon didn't quite follow the pattern of the other stars. He had some reasons. However, his explanations fit just a particular time. Later, inconsistencies grew up in the system and became more and more complicated to explain. Okay? Harder and harder to figure out. Now remember, these were the ancient Greek astronomers and philosophers. This, at the moment, had nothing to do with Christianity, except for the fact that the late Jewish and early Christian time followed very quickly after the Greeks. So a lot of Greek ideas made its way into Christian belief, okay? And suddenly the church got involved with it, and they came up, and I've never found them, some sort of scriptures they think indicate that God said the earth was the center of the universe. I don't think it's there. I've never seen it, but that was their belief. Well, they got it not from Scripture, but from the Greek philosophers and astronomers, okay? But boy, once that was there, it was entrenched. Badly entrenched at that, okay? Now, along came Copernicus. Now, here's the interesting thing about Copernicus. I didn't know this until fairly recently. I just knew he was a scientist who, one of the earliest ones to propose the Earth is not the center of the universe, not the center of the solar system, but that the sun was the center of the solar system. Now here's what was interesting about it. The main proponents of this was now the church. Not necessarily scientifically based, but religiously based. So you didn't go against the church. Well, guess who Copernicus was? Back at this time, this was probably late Middle Ages, getting out of the Dark Ages into the Middle Ages, beginning of the Enlightenment, you might say. Well, at that time, most of the educated population in Europe were the clergy, because no one else could go to college. I mean, the church controlled the universities. But Copernicus was quite a good mind, but guess what he was? He was a monk. He had been trained in science through the church. But he did a lot of observations of his own, brilliant, brilliant mind, and he said, hey, this doesn't jive. And he wrote up his work but refused to publish it because he knew the church would oppose it. So he wrote it up with, I don't know if he had strict orders that it never be published, but it never be published during his lifetime. And his assistant, who came after him, after Copernicus died, he published it, okay? I think under Copernicus's name, but he was dead now. The church couldn't do a thing to him, okay? And that's when along came Galileo, and he read Copernicus's work. He was impressed by it. It made sense to him. And then with his new telescope that he created and made it so much more powerful than the earlier ones, he saw the rotation of Jupiter. He saw the rotation of the sun. He saw the moons around Jupiter. He realized our moon was going around us. And if we were indeed rotating like the other bodies, that's what gave the apparent appearance of the fact that the stars revolved around the earth. No, they didn't. Or that the sun moved around the earth. No, it didn't. And now, with the heliocentric model, meaning sun-centered, that the inconsistencies that were abounding more over time of the geocentric model were explained by a heliocentric model. And here's one of the examples of why the geocentric model just didn't work. Okay? Now we know the sun's in the center of the, or near the center of the, well, basically the center of the solar system. Here is the Earth going around the sun. Now, they didn't used to think this, but it was. Here's Mars going around the sun also, but outside the Earth. So say you're here on Earth on this night here, and you look up and you see Mars. Come on, my cursor went away. You look up and see Mars, and there Mars is, because there Mars is in its orbit, so Mars appears to be in the celestial sphere right up here. The next night we've moved to here. Mars has moved much more slowly, but moved to here, so now Mars seems to have gone here. Well, yeah, that's following a pretty good pattern. And then the next night, we're here, Mars is here. Yep, following a pretty good pattern. The next, and this isn't nights, but next some period of time. In fact, this must be months apart. The next month, Mars, we're here, Mars is there, so it appears there. Well, so far, Mars is changing speed a little bit, but seems to be doing all right. But then the next month, we're here, or it may not be a month, some period. Mars is there. It's backed up on itself. It was coming along this way in the night sky, and then everything else follows the regular pattern. Mars turns around and backs up. And then the next time we're here, Mars is there, and now it appears to be there. And then it picks up again and starts on a regular pattern again, a lot like it was here, because we've changed our position as Mars has changed its position. And that made Mars sort of wander around the night sky in an irregular manner. And by the way, the word planet comes from the Greek word wanderer. It's wandering around. It's not making any sense. It got lost and backed up on itself and then found itself and took off again. That's why they called the planets the wanderers, the planets. Okay? Now, I think that's what Copernicus must have observed, and he said that can only be explained if you put the sun at the center and we see Mars, and as we're moving...
It's 6:15.
What's that?
It's 6:15.
Oh, is it? How could it be? Okay. Let's see where we are in the book. Okay. We'll pick up with this slide here. So we'll pick up with heliocentric model next time. I'll repeat a little bit of that, but not too much.
Can't hear you.
Okay, I said we'll repeat a little bit of what I just said, but not too much. We'll pick up with this slide next time. Okay, where have we got to go from here? We've only got a couple pages more in chapter 15. So what we'll do next time is start with chapter 15, and we will go from 2:30 until 4:30. At 4:30, we'll stop wherever we are in chapter 16 and have a full 2-hour lab. No, I'm sorry, 4:15. We'll stop at 4:15. Normally stopped at 4:45. We'll stop early at 4:15 and have a 2-hour lab, and I think we'll be able to get the entire lab in. Now, it's a little bit different lab from what we did last time. It'll take us a little longer to do. It's going to be a multi-page lab. I don't know how many pages, about 7 pages. This is one that came out of the lab manual. The last one I picked up off the internet and made up my own lab. This one will be one we'll be working together. So if you can, try to print the lab before class begins. You won't need anything else but the lab, and we will work on that together. Okay? So this will pick up, and so like I said, we'll finish chapter 15, starting at 2:30, and only go until 4:15. At 4:15, we'll stop, and then we'll do the lab. We'll have a full 2-hour lab, not an hour and a half lab. Is that okay?
Yes.
All right. So we'll see you next time, and that will be next Monday. So have a good weekend, okay?
Thank you. You too.
Okay, and there's nothing you have to turn in today unless you do the first lab or the test. That's all. That will cover you for the week, doing that lab and test. And then next time we'll have the second lab. From here on out, you don't have to make up something to turn in. It's either going to be a lab or a test or both. Okay?
Okay.
All right, good deal. So I'm going to stop the sharing. And there's Valerie. And there's Henry. So let me end the recording and end the meeting for all. And we will see you later. Oh.